Hello, everyone. So thank you for being here today. So for the next 45 minutes, I will present you the methodology I use for a few years now to tackle down fully hardened information system without bringing any other tools on the target that what it's giving to me. So the other name I had for this talk was Perform a Red Team in a point and click. So it's this name because in this talk we will compromise a full Active Directory environment without touching a Windows system or on-premise assets. We will move from being an attacker to being the best sysadmin they ever had on their information system. For attacker, you will find a framework to start attacking information systems that seems unbreakable, and how to manage having an impact when you cannot use your default tools or any attack tools you usually used. For Defender, you will learn that what is left to be secured once you have finally secured your Active Directory environment and remove all the low-hanging fruits you had on your environment. So, first, let me introduce myself. So, my name is Johan. I'm a red team leader at Waystone for 6 years now. So it's a French consulting firm. So I dedicated my time to large-scale red team operation and development of internal tooling, mainly malware through, for example, Cobalt Strike, new malware development technique, and things like that. So for this talk, we will take as an example a hardened information system. So this is the information system everyone wants to have. It's an information system where the Active Directory has been fully hardened. You won't find any privilege escalation directly based on the Active Directory. If you run a blowdown or a ping castle, you won't find anything. The network segmentation has also been hardened. You won't find any administration services exposed directly on the information system. You won't find administration application or things like that exposed directly in the information system. So even if you find some unsecure credentials, you won't be able to use them because you won't have the endpoint to use them. And the last one is the detection and response. These companies have the best EDR system, best network probes. They are all configured, well configured, and all the events are correlated in the CM. So even if you find an exploit, even if you are able to access to a system, you will quickly be detected, your event correlated, and all your entry points removed. So it's a strong security baseline that everyone wants on their information system. The question now is, as an attacker, what can you do? You have been missioned with a red team on this environment. You have 6 months to compromise this environment. What can you do without being detected on the first day? And all this talk aims to give you the clues to start your operation and see how you can move out from this contained environment. What are the lever you can use to go on the control plane and try using the control plane to evade every security solution that has been set up in the environment. So when you want to go from the data plane, so by the data plane, I talk about all the applications that are in the information system that are usually accessible to any users, everything that contains the data. The control plane will be everything that is related to administration, everything that is used to manage the system, to virtualize the system, or everything that is not supposed to be accessed by a standard user. So when you want to pivot from a data plane to control plane, you have to find an application that is a limit of both elements. You have to find an application that is accessible to any users, but will have impact in the control plane. Such applications can be some automation application, no-code application that are exposed to every user because they need it for their work, but will impact other servers. A right example a few years ago was the data science applications, because these applications were used by standard users, but used to execute Python script behind the servers, and they could be used to break the isolation between the data plane and the control plane. Today, the most interesting one is a CI/CD application. Why the CI/CD? Because the CI/CD is not an application, it's a pipeline of multiple applications. So it's easier for it to have a foot in the control plane and a foot in the data plane, because we will have some applications that have to be accessed by standard users, but by definition, the CI/CD must also manage infrastructures and configuration, so it will have impact on the control plane. Because it's a spectrum of application, it's different application linked each other with trust and network link. You have more chance to find an application that is less wrongly configured, or somewhere you will find a hand to start your exploitation. So quickly, how does the CI/CD work? It's quite easy. You will have an administrator and a user that has developed a code. It will store the code in the code depot. Once he is happy with the code, he will create an artifact and store this artifact in the Artifactory or other application like that. Once the release has been pushed in the Artifactory, the deployment engine will fetch the artifact, give them to the runner, and the runner will deploy this artifact in the different end applications. And this is where you can see that CI/CD is really important, because while the user didn't have network access to the end application, for example, the IAM application, the GitLab application, or the SAP, the runner can then access to this application. So if the attacker, the user crafted a specific packet, he is able, from the data plane, to directly impact assets in the control plane. The other thing is that the runners also have a lot of privileges, either network privileges to access administration services, but also privileges to deploy code, privileges to deploy applications. And if you are able to hijack the identity of these runners, you will be able to move directly from standard users to T1 administrators. So this is why CI/CD is interesting. The other point is what I said before, is that you have a lot of different applications that will be exposed to every users. The GitLab is more and more exposed to every users because company thinks that everyone should be able to create their code, participate to the code, share snippets and things like that. The Artifactory is also more and more exposed in the user in the data plane because some companies want to manage, for example, Python packets, and will put these Python packets in the Artifactory, and people will only be able to get the Python packet from the Artifactory. So they need access to this application. So it gives you a lot of attack surface. And this attack surface doesn't need any code or any exploitation. To be used. The first level of exploitation is the one that everyone does, is looking at the code, understanding how it works, finding secrets, and finding technical data. You can say whatever you want. If you have a code somewhere in your information system, you have an unsecure credential or an unsecure knowledge in your code. And this is a level 1 of CI/CD exploitation, and it's not the fun one. But when you access to a GitLab or Artifactory, the first thing you can do is just by clicking on the different link, trying to understand what is this code, what is the application behind, how it works, what are the assets impacted, and starting mapping your information system without even needing an Active Directory dump or Nmap scan or things like that. At the moment, you will find the secret. It's not a big secret. It won't be a domain admin password, even if we already found a KRB TGT account in a GitLab. But you will find a small secret that will allow you to have an impact, a small impact on one of the CI/CD chain. Usually, what we find is an Artifactory token. This token is not interesting by itself, but it allows you to update an artifact in the Artifactory. It is usually set by developer in the GitLab pipeline in order to automatically deploy their artifacts. Oh. And this is exactly what we will do. Once we will find a way to impact any element of the CI/CD pipeline, we will start injecting ourselves in the standard execution flow of the pipeline and trying at each step to have an impact on every application we are going through. So the standard way is, for example, pushing a malicious update on the Artifactory and waiting for a deployment or forcing the deployment. The deployment will retrieve the artifact, and the runner will start exploiting, will start deploying the artifact. And this is at this moment that you will have full impact. The first way is trying to have remote code execution on the runner. This can be done, for example, if the runner deploy infrastructure as code, you can use Ansible or Terraform primitives to execute code. The other things you can do is push an unsecure configuration change on the end application. This is funny, this is impactful, because if you succeed to changing the configuration, for example, of the IAM application, you will be able to get additional privileges and finalize your operation, but you are still in the data plane and we want to go deeper in the control plane. That's why the execution in the runner is the most interesting one. It's the interesting one because it will grant you a full network access to the information system, or at least a wider access than you have. You will be able to harvest a lot of credentials. Either credentials are coded in the runner or in all the projects that will go through the runner. And the last one, the last gift, is that usually runners are not static machines. They are deployed in a scalable environment, either Kubernetes, AWS, Azure, and things like that. And this is really interesting because in the cloud environments, everything is identity. And the runner is an identity in the cloud. And once you have this first identity in the cloud, you are able to start your cloud exploitation. So the cloud is really interesting today because its level of security is the same as Active Directory 10 years ago. It's something that is widely used. A lot of people use it, try to secure it, but you have still a lot of flaws that can be exploited silently. The other thing is that cloud security is really hard because every exploitation, majority of the exploitation is based on IAM. So when you are trying to secure the cloud or detect an attacker that has an entry point in your cloud environment, you don't have to search for someone exploiting resources, someone performing CVE or things like that, but you are starting to look at users that have specific privileges, trying to use these specific privileges, and you can't differentiate what is normal use and what is attacker use. And this is really where having an access to the cloud is really important for an attacker, because it's an area that is not under supervision, where you will be able to retrieve secrets, retrieve access, and retrieve knowledge about the information system. And once you will have all this information, you will be able to go from the control plane back to the data plane with all the credentials you need to authenticate to the domain controller, for example, or authenticate to a critical application. So the first technologies we will see is AWS. So on AWS, as I said, everything is identity. When you have a computing resource in AWS, it has an identity. This identity has a role, and the role grants privileges. This is how AWS works, and this is how most cloud environments work. When you had a remote code execution on the runner, you had a remote code execution on the underlying Linux system, but you also had the capability to extract the runner AWS identity and use it for yourself. And the runner AWS identity has usually a lot of privileges. The first one will be the deployment of resources in your cloud environment, because if you have an infrastructure as code, the runner is tasked to connect to AWS, create the resources, configure them. If you hijack the runner identity, you will be able to also access AWS, create resources, destroy resources, and change the configuration. And this is exactly what you will do. Once you have an access to AWS, the first thing you have to check is the different access you have to the different resources. The main resources will be, for example, the Lambda, the role, and the secret managers. Sometimes you will find some accounts that are used to link AWS computing resources to the Active Directory on-premise. And the secrets will be stored in the secret manager, and you will end your red team like that. But sometimes you will also find some Lambda code that has been deployed by administrators, and this Lambda code will have a lot of privileges because they will create other IAM users, they will change privileges over a role, things like that. So you will be able to access the Lambda, hijack the identity, and reuse this identity to perform additional things. The main goal in these steps is enumerate your account and trying to elevate your privilege to the admin access account. Admin access privileges. Admin access privileges is the same as a domain administrator in Windows. Once you have this access, you can have access to all resources in the account, and the most important resources is the IAM. The IAM is a document that contain that explain all the trust there is between resources in your account. So when you have a knowledge of the IAM, you know exactly what are the privileges of all your roles, what are the privileges of all the resources, and what are the privileges of your resources in another account. And this is really interesting because it allows you to perform a lateral movement from your initial account to a most interesting one. For example, the runner identity usually deploy machine directly in the production account. With the IAM, you will be able to understand this and perform a lateral movement from the standard AWS account directly to the production account and have impact on the production machine. So this is quite all you will do in AWS. So this is really interesting because it's a point and click. You go in the different menu or with the AWS CLE and check if you can access the different elements. The other thing that is really, really interesting for an attacker is that even if you raise a lot of logs, today security solutions have troubles to detect resources that are using their own privileges. They will detect change in policies, they will detect unsecure access, but they won't detect a runner, for example, that is starting to deploy resources it shouldn't deploy. So even if you are browsing all the resources in the AWS account, there is great chance you won't be detected at this step. So what you will do is that you will perform lateral movement against the different accounts more and more until you will find an account that we can call IAM routing. The IAM routing account is an account that is usually created by companies to centralize the identity of all the users that will have access to AWS. And among these users, you will have all the administrators, the AWS administrators. With all the privilege escalation you have performed all along, the knowledge about the AWS environment you have retrieved, and the secrets you have gathered during your journey, you will likely arrive in the IAM routing account with enough privileges to spoof the identity of a user. And spoofing a user identity in cloud environment is really easy, because you can create an access key, you can create an SSH key, you can assign the identity of a user to a resource you manipulate, or a resource you have already compromised. You have plenty way to spoof a user identity. And if you are able to spoof an admin identity, you will be able, not the right way, you will be able to access to the organization account. The organization account in AWS is like the root forest in Windows. All the accounts you have compromised until then live inside the organization. Once you have compromised the organization, you are able to go back to all the different AWS accounts with maximum privileges. And this is at this moment that you have fully compromised the AWS account. You can think that I'm just imagining these scenarios, but it's something that happens every time. Sometimes we arrive in AWS account with a runner identity or a standard identity, and in one hop, we arrive in the organization. Sometimes we have to compromise 5, 6, 7 different accounts, but every time we are able to find an identity that is that has too much privileges, that is not controlled, that have impact on resources, and allow us to perform this exploitation path. So this is a way to compromise AWS, but our final goal is to compromise the Active Directory. And this is where having impact on the control plane is really interesting. Because when a company uses AWS, they often also deploy their tier 0 resources in AWS. For example, they can deploy their domain controller in a specific account that is segmented. They can deploy their IAM application directly in AWS. They can deploy their GitLab or every critical application you think of. It's possible to find it in AWS. And once you have compromised the AWS organization, you are able to have impact to the data plane without, you are able to have impact on the data plane and bypassing every security solution that has been configured to analyze the data plane. And in this case, if you have compromised AWS, you are able to retrieve the different domain controllers instance, retrieve the disk, create a snapshot of this disk, exfiltrate this snapshot in another AWS account you control, mount this snapshot, and extract the NTDS. And this takes literally 5 minutes to do. It can be done with a mouse and 3 clicks, and it's not detected by standard security solution, because CrowdStrike is deployed on the domain controllers. Your EDR solution is deployed on your domain controllers. Your network probes is deployed on your network. Nothing is protecting your cloud. The only security solutions you have in the cloud today have troubles to detect privilege escalation. They will likely today detect the creation of a snapshot, but most of the detection are based on posture control and not exploitation control. And even if there is a detection, you will still have your Active Directory snapshot all the secrets in them, and it will be a hell for them to get you out of the information system. The other thing is that in AWS, sometimes the company doesn't know really well how it works. They don't know what is the impact of cutting an account, what is the impact of changing a policy, and you will be, even if you are detected, you will be untouchable because they won't take the risk to shut down all their information system just because they detect a low signals. So the first thing I do when I start a red team operation is understanding what is their cloud environment, is it secured, and how can I access it with high privileges? Because once we have access to AWS with high privileges, it's usually the end game. It's usually the end game because you can make some move from AWS to Azure or AWS to other on-premise assets. For example, the main things we find in AWS is the GitLab. When one part of the CI/CD is deployed in AWS, the other part is also deployed in AWS. When we compromise the GitLab, we are able to retrieve all the different secrets that are stored in the pipeline. And among the secrets, we will find the entry key to the Azure environment, which is service principals and app ID app secrets. These app ID app secrets are really the best way to have an entry point in Azure because they are often overlooked by developers. We often find some client secrets, client ID in network shares, in application source code, or unsecurely stored in a computer. They are overlooked because a lot of people doesn't know that even if you only use your app ID app secret for SSO, there are a lot of privileges that can be attached to your client ID, client secrets. So like in AWS, the initial point in Azure is performing an enumeration of your resources, trying to understand what happens, trying to understand what is the reach of your application secrets, and what you can do in the different subscriptions. And the idea here is finding additional users, finding additional application secrets that will have more privileges than you already got. And every time we finish by finding the most interesting application in Azure, which is an application that has the site read-write-all and the file read-write-all privileges. Those two privileges are really interesting because they allow you to access to all the files that are stored in the SharePoint. And when you have access to all the files stored in the SharePoint, you also have access to all the files stored in the user's OneDrive. Usually, with this level of privilege, you are not domain admin, but you have the most important impact on the data. You can retrieve all the confidential data of the account, all the critical data. And with the OneDrive access, you will also be able to access to all users' personal files, every kdbx.csv, all keypass.xlsx, every extract of password the user has done once and forget in the OneDrive, you will be able to access it. And this is what happens. With the SharePoint, you will be able to browse different files, retrieve different secrets. You will likely find better app ID app secrets that will also have access to Outlook or Teams. In, I think, 75% of our red team operation, we end with an application ID that is able to access to the full SharePoint, all Outlook mails, all Teams mails, all Teams message. And with that, even if we are not directly domain admin, we have the control over all the operation. Because even if we are detected, with the impact on the mail and the Teams, we are able to know when a ticket is opened by the SOC, we are able to close the ticket, we are able to remove the message, remove the alert, even connect to the Teams conversation of the SOC that is discussing about the incident. So the other thing is with SharePoint, even if you don't find sensitive information, you will find technical information. And this is also really important because the technical information will allow you to understand how the information system works, how the administration is performed over the information system, and how you can inject yourself in the administration flow without raising any alerts. For example, some SOC team use some EDR features to perform real-time responses. They use a token and a script to execute remote code on the different assets. Having access to the SharePoint allows you to understand how this is done, where the secret is stored, how it is accessed, and how you can use to access to the secret as a standard users. And this is exactly why SharePoint is really dangerous. It's not dangerous for the secrets, it's dangerous for all the technical stuff you can find inside. All the technical stuff you will find inside. The other thing is OneDrive. In OneDrive, Microsoft likes to synchronize everything. So if someone just creates a file in the desktop at the moment, it has been synchronized. The file hasn't been fully deleted, so the file still lives in OneDrive. And the thing we saw a lot is someone that is starting to change their computer, exporting all the Chrome history, all the Chrome password, exporting their LastPass or their KeyPass, putting it in their desktop for a few minutes, but the file has been synchronized in OneDrive, and we are able to retrieve all these credentials for free in their OneDrive. The other thing is a configuration file for administration tools, such as mRemoteNG or FileZilla, that contains all the credentials that can be easily decrypted and allow you to manage the information system exactly as the administrator would have. And this is where it's hard for the SOC team to detect. It's because you will use exactly the same tools than the administrator to compromise the information system. You won't compromise the information system, you will administrate it. You won't, So, with this level of privileges, it's time to go back in the information system. You are full stuff. You have credentials for everything. You know exactly how the information system works. You know what are the hosts that are under supervision and what are the hosts that are not protected. So the first application that I like to target is the EDR consoles because it's a free command and control that has been deployed on the information system, and once you have compromised the EDR consoles, you will likely be able to execute code everywhere in the information system. If you find the last EDR consoles, they are SaaS applications, they are linked to Azure environments, and with your level of access, you usually have all the privileges needed to connect to an administrator workstation, dump the cookies, or hijack the sessions and connect to the EDR console. The other thing is that EDR console are also accessible from the internet. So if you have access to, if the EDR console hasn't been fully hardened and you are able to find an initial access in the EDR console, you will still have access persistency even if you are put out of the information system. Okay. The second thing I like to tackle down is IAM application. IAM application are more and more deployed in the information system to allow self-privilege for ticketing, to request privileges and things like that. In the IAM application, it's usually applications that are hard to fully secure and deploy securely, because you would like to add some specific features that will create a bug, that would create a flow that can be exploited. The most important one is the ticket auto-validation. More and more, we saw some IAM applications that were configured a few months ago, few years ago, and the validator for the specific roles are retired or not here, the identity has been removed, and it lets a privilege without any validator. So if you find such privileges, you will be able to ask for the privileges, validate yourself, and retrieve the privilege by yourself. Usually it's not very important privileges, but it can be privileges that will open you access to a specific network shares, that will grant you access to the GitLab and allow you to start the exploitation path. It will be something that will help you during the exploitation. The other thing is that it's less and less true, but IAM application were for a big time managed as tier 1 application while they were used to manage tier 0 application, a tier 0 identity. For example, you were able to ask for domain admin privileges through the IAM application. And the person that will validate your ticket or the person that has created the validation flow is a tier 1 administrator. So you have a break in the tiering model at this level. And the last one is relating to monitoring. IAM applications send a lot of mail. When a user requests a role, when a role has been granted, when a role has been validated, and even if you ask for something, the mail will be sent to a mailing list with 20, 30, or 50%. And everyone will think that someone else will act on this alert. And you have the bystander effect, and all the alerts you have raised won't be processed by the security team. So, yep, here we go, yep. So maybe the conclusion. So the idea behind this talk, as you saw, we didn't use any technical tools. We didn't use any exploitation tools. We didn't find any CV or any 0 days. But it's the idea. When you want to be stealth, you try to limit your exposure. You try to limit the tools you will use, and you try to use as much as possible all the tools that are given to you by the information system. And the tools can take many forms. It can be a binary, it can be a set of applications with, for example, the CI/CD. It can be a full environment with a cloud. It can be a token, secret. It can be anything. The idea is that when you are starting your red team operation, don't try to exploit something. Try to understand how everything works. Try to understand where to push to have the maximal effect. And 80% of the time, you will see that you don't need any relay attack. You don't need to have a beacon in your servers. You can just click on the link and try to elevate your privilege like that. So what you can do as a defender against this? The first one is extending the tier 0. It's something that is known for years, but not really well done. Tier 0 is administration model created by Microsoft for the Active Directory, but it's an administration model methodology that can be applied to everything. When you think about tier 0, do not think about assets. Think about everything that have an impact on the tier 0. The tier 0 is contaminating. Something that touch a tier 0 asset is tier 0. In the tier 0, you have your domain controllers. The domain controllers are managed by the domain admin, so domain admin is in tier 0. The domain admin privileges is granted by the IAM application, so the IAM application is in tier 0. The IAM application is managed by specific users. These users are also in the tier 0. And you will see that a lot of identity, a lot of assets you found, you thought was only low privilege, have a lot of privileges over your tier 0 members. The other thing is that deploying tiering model on every application that have privileges. The tiering model is for Azure, is for Active Directory, but you can deploy it on your cloud environment. You can deploy it on your CI/CD pipeline. You can deploy it on every application that have privileges, that have a system of rights, and a system of administration. And the last thing is the segregation between pre-production and production between all your environments. The idea is that you must be able to cut the access of the users to a limited part. The second part, it's something that I think is put in every red team report, every pentest report since 20 years. it's credential storage and management. You must invest in secure vault solution. It can cost a lot, but it will allow you to have managed secrets, rotating secrets. It will allow you to limit the passwords that will leak in the code depot in the application. It's an investment that will have a lot of impact in your security level. Once you have secured your credential usage, the next part is assessing the blast radius of all your credentials. You can have your SQL account in your CyberArk, but if this account has administration privileges over 70 different SQL servers, the blast radius of this password leak is really important. If you use one password for a specific set of applications, if this password leak, the impact will be limited and the attacker will have to go back to the beginning in order to continue its exploitation. The third one is IAM policies and privilege. This is the one that is the most complicated to secure and the most easy one to exploit. Because because a role by itself is not dangerous. Which is dangerous is the accumulation of the role, the accumulation of the privileges. And it's not something that can be easily seen in any application. If you look at your IAM application, you won't be able to see directly all the link of all the roles and all the privileges granted to the users. And more, we can see that standard users, through accumulation of privileges, will have too much privileges and no one would know about it. And when this user will be compromised, the attacker will be able to use these privileges to perform lateral movement, privilege escalation, and compromise your information system. And all your security solution will find it normal because it's a user that is using his own privileges. So what you should do, it's quite obvious but not really simple to do. It's review the IAM process to avoid any auto-validation, any roles that are overpowered by the IAM for the IAM application. You have to implement the separation of power, and you have to perform recertification of all your users on a regular basis. You can't let user with high privileges retrieve once to keep it for all his life. These privileges must be recertified. And the third one, it's the middleware hardening. I took the cloud and the CI/CD as an example, but another example will be the SQL servers, the MS SQL servers that are linked to each other, that create a cluster, that are not secured, and that allow an attacker to perform lateral movement easily by using linked you have configured by yourself. So middleware will be, I think, the next way to put your effort once you have secured your Active Directory environment. Because the middleware is not well protected by EDR solutions, because the EDR solution won't know if it's normal for this Java process to create a new process or it's an exploitation. You won't know if it's normal for these SQL servers to connect to a remote SQL servers, etc., etc. So that's why you have to harden your middleware as much as possible in order to limit your attack surface and avoid an attacker to use them to compromise your information system. So I know these recommendations are quite large. They are quite the same thing that you will have in all your pentest report, and you think you have implemented them, and every time you find a new flaw. And it's where it's really interesting is that attacker, while they evolve, they still use the same pattern. They still use the same technologies and techniques. The only thing that change is the support where they are using these techniques. So, yeah, thank you. I don't know if you have any question. I think we have 5 minutes for the question. I hope you enjoy the talk, and I think you have a mic, I think.
Yeah, it's when you're forced to perform like code execution, are you going like down a C2 route or are you using a proxy?
I'm not hearing you, sorry.
Okay. When you're forced to do code execution on like systems, if you're trying to like either, I don't know, you have to, you're forced to, are you going down the C2 route or are you doing are you using like a proxy like Chisel or something?
So the question was when I have code execution of on a system, do I start a beacon or do I try to use another tool? Usually I'm using more some socks than a full command and control because the socks allow me to plug all my tools and limit the exposure I have on the information system. Few years ago, I used a lot of SSH to perform reverse proxies. Now today, this is a trick that is well known by security solutions. But yeah, you can find a lot of lol beans that allow you to create some socks or have remote impact. Yeah.
Have you ever tried to attack MuleSoft middleware? Okay. It's Salesforce. Okay. Yeah, MuleSoft. Yeah. Thank you.
Yeah. Yeah, the question was if I already had access to MuleSoft or Salesforce. The answer was usually on Salesforce it's more like I already got impact on a user that have a lot of privileges over Salesforce, and I just hijack his identity and access to Salesforce. And more and more what we are finding is applications that use Salesforce to retrieve objects, retrieve files, and this application, the Salesforce hasn't been fully secured, hardened, and this request allow us to fetch more data such as prospect, clients, and things like that.
Everyone staying adequately hydrated at this point? No? Okay. You do need more water. You need a lot more water. Okay. So, quick show of hands. How many folks do we have that identify as red teamers in the room? Blue teamers. Management sods. Other or miscellaneous. Any GRC nerds? You're a larval cybersecurity person. Fascinating. So, what if I told you that everything that you've been taught about how pen testing and red teams actually work is complete and utter bull? So, we decided to get some ground truth data on this. Over 95 engagements, shot over 6,000 commands, and we came up with some interesting bits. So what we learn about out in public, in the reports, is essentially self-described war stories. It's by vibe. It's the things that we drew for the management types because they like nice step-by-step and not the actual fuzzball that it is. Across 95 internal pen test engagements, we recorded every single bit that crossed the screen and was typed by the operators for later analysis. And we were able to use this to extract not just temporal, they did this, then this, but the causal flow. They learned something from this command, which led to them being able to run this command further downstream. And that gets a little interesting. So we used ASCII cast, ASCINema, tied it into tmux. So every time one of the testers launched a new tmux window, we got a clean session. And put all that together. There's some back-end stuff that I'm happy to talk about later if you'd like. There's plumbing. There's always plumbing with this kind of things. But this gave us everything that the tester saw during the engagement, everything they typed, everything that flashed on screen, to the millisecond timing for it, no matter how many different windows they had up and running. So what we found, among other things, pen testers love using tmux. The top view was 55 distinct tmux sessions inside that, averaged out at about 13 per engagement. Not a single one only used a sole view. If you're like most pen testers, you are probably off the scale on the ADHD, and you cannot single task to save your life. That's all fine. We took this data and extracted out of the tool output 11 different entity types. So IPs, host names, usernames, domains, paths, hashes, all that kind of fun stuff. We were able to correlate that information to, is it something that is consumed by a tool? Is it something we pass in as in a file, or out of that, is it something that's produced that we discover? So we could keep track of what a pen tester knew going into the engagement, typically the scope, IP ranges, and what they learned along the way that enabled further tool use. And that enabled us to build a causal graph structure. So we all know and love Bloodhound and going through Active Directory that way. But you can graph out the individual bits of information that one learns during the engagement and then use that to track how commands and options open up as you discover things. So we used, at the time, Claude Opus 4.6 is our analysis middleware here. We straight up fed the entire ASCII cast file into that, the consolidated view across all of the sessions. It turned out to be the best possible way for us to extract that information. We had tried experimenting with terminal reconstruction and doing some regex stuff, and we all know about regex. You know, you solve a problem with regex, now you've got like 17 other problems. So we were able to extract the semantic entities, success or failure detection on the command. Did it actually complete successfully? Did it throw an error? Did it just silently go, yeah, nothing new here, move on? Running it through the LLM gave us a 64% improvement in the classification of what part of the MITRE attack framework is being exercised by any given command. It also enabled us to consolidate the different names for entities, because you might have a particular host that you use one command on that's an IP address, another you use a host name. Collapsing that down to refer to the same entity actually improves quite a bit of this. We're damn near 100% classification accuracy on the LLM, as well as entity extraction. Some poor sod had to go through and hand review everything that came out of this to produce that bit. So these are 95 engagements that were conducted by one consultancy over a period of about 2 years. So we've got a variety of technique changes and improvements across this. Everything was de-identified, aggregated, and the customers that this was being done to were aware that we were recording this for science. So we've got some hard definitions. We observed oscillations between different classes of things, not clean pathways. When we talk about causal edges, this is where Command B could not have possibly been run without knowledge obtained from the execution of Command A. So we can call those, say that there's a causative link between the two. The density of the causal edges, causal edge divided by the number of commands executed. Obviously, the ratio between the two has some interesting properties that we'll get into this. So again, this is from a single organization that, despite having common procedures and TTPs, no two testers do the job the same way across that. These distributions are skewed by that. That's part of the reason why the entire analysis pipeline and toolchain, we're making that available under an MIT license, so that if you feel froggy and want to record your pen tests this way, you can run the same analysis. And I would be very, very curious as to the results that you get out of that. So before we get into this, I do have a 0th finding. Pen testers can't type worth crap. This is consistent and universal, and that's part of what led us to leverage LLMs for the analysis, because it could go through and take the 15 times that you mistyped NTLM relay X and actually consolidate that down into you actually ran that one thing and didn't have a cat walk across your keyboard. But the real first finding is that these attack paths, this kill chain, isn't a linear chain. It's actually a spiral that oscillates between two specific phases. So the common pattern is you find something, then you get some credentials, and then you explore with the credentials, and then you find more credentials, and you keep oscillating between those two phases until you get to something that is the breakthrough command, the breakthrough action, what gives you escape velocity out of that loop. So what we've got here, the heat map represents the transitions from one command to the command immediately following that, bouncing back and forth between the different MITRE attack mapped phases. So we have the nice angry red that are going back and forth between credential access and additional discovery. There are other slightly stronger but nowhere near as strong transitions that are commonly occur. But on average, a tester is going to bounce back and forth between those two phases 12 times before they actually get to anything that's remotely priv-esque or lateral movement flavored. So that's kind of special. So looking at this another way, just visualize in your head, they keep spiraling around toward the end of the engagement, and eventually they'll either crash into the surface and they don't get anything really accomplished, or they find something that lets them jet off into lateral movement, privilege escalation, etc. So these transitions, it's hard to convey in a still. So I brought a home movie. The squares are commands. The color-coded by the MITRE ATT&CK mapping. The circles are the individual knowledge nuggets. Down here in the bottom, you can see the commands that are getting executed as we go. And we'll just take a minute to run through a relatively representative internal Active Directory engagement as we start seeing tool use that leads us to bits of information, which in turn starts turning into actual attack paths that we can leverage. So a little bit different view than the classic, Bloodhound running through the network graph. A lot more disconnected, but you can get some ideas of how the discovery expands out. And this was like a week and change engagement that we're consolidating down into 30-ish seconds through that. So within this, your pen testing methodology is more of an iterative refinement loop, not a linear progression. You're taking the things that you did not know before, and then that is expanding your options for what is allowable. When we teach people how to do pen testing, it's often, here's the SOP, run these tools in this order, and then magic will happen. It's almost like it's like a Julia Child's recipe. Okay, you follow it and you will get something that is vaguely shaped like a actionable pen test report at the end. But the reality is there's a lot of head butting and head scratching and keyboard throwing and whatnot throughout the course of a typical engagement. And we don't, as an industry, train people to deal with that. So you get a lot of frustration and all that. Measuring cycles to exploitation is, I think, a better metric based on this data set than the number of phases that are covered within attack. And generally speaking, the fewer cycles, the better the operator. They have that sixth sense about the things, or they're very, very lucky. Both are a thing. Things fail more often than they succeed, clearly. Extracted failure versus success by MITRE ATT&CK classification. The deeper you get into the exploitation of the network, the higher the probability it's going to fail, not work, generally blow up in your face. Lateral movement attempts failing almost 60% of the time was a little bit of an eye-opener if you've just been staring at your test reports. So most common failures, netexec, certify, NTLM relay X. Your reports, they're the rah-rah, this is what we did, this is how we got to whatever our objective was. They're not based around, okay, these are all the things that failed. Generally, you only are reporting on all the things that failed if you don't have any actual positive findings. These are the things that were adequately covered for with your compensating controls. Go you. But these failures give opportunities for additional detection. So in a lot of the detection surface, there's significant noise around this, but it tends to be concentrated from specific entities. So if you are, from a defensive standpoint, looking at those concentrated failures, that provides incredibly strong signal. Now, most of the entities that were tested in this period ranged in maturity from 30 to 50 person small shops where you might have an outside MSP, all the way up to large publicly traded organizations. Even when we asked the defenders to let us know when they saw things, they didn't see a lot of things because their detection surface was kind of shallow. Notes out of this can help with that. concentration, that exploration phase, anomalous behavior provides a nice rich detection surface for further exploration. Now, when we look at it, the actual host names have a lot of additional semantic meaning, and those are the real bottleneck in the testing. When you're looking at list of IP addresses, there's no context around it unless you can infer something from, okay, all the domain controllers are in this subnet, and all the file servers are in this subnet, and all the database stuff is over here. When you get the host name linkage, you can most organizations have some kind of nomenclature where it actually is reverse engineerable what the heck a thing is. You've got DC01 versus file server versus a workstation, or they just use the generic Windows names, or they have some kind of mythology-based or Marvel characters or whatever nomenclature for naming their servers. Bigger the organization, the more likely there's semantic meaning attached to the domain name, to the host names, domain names, etc. When we did the resolution between the host name and the IPs for the modeling, a lot of interesting bits correlate out of that. So when we look at it, 40% of the graph structure that we end up utilizing here is invisible unless you're collapsing all the many names of the particular thing into there. So you could have a hardware MAC address depending on your attacks, or IP, or host name, or this other host name, or this other C name that's being referred to that's pointed there. When you collapse all of it down, you start seeing the true attack structure. The blue edges did not exist until we collapsed the host name and the IP address for the analysis. So that leads us to those breakthrough commands and operations that give us escape velocity away from that loop and cycle. Now, this is kind of dense, but normalized for time, this is every single one of these engagements. Going up vertically is the amount. Once you get to that breakthrough point, generally speaking, there's not a lot more to learn in the environment, no matter how hard you pound at it. And I am not, as a recovering pen tester myself, I am not going to say that you get DA in the first day and you stop right there and it's time to write the report. No, you want to, but that's actually what tends to happen. So typically we're seeing either like a mass net exec, or they manage to get credentials to do DC sync attack, or Bloodhound, Sharphound, whatever. Now, the best attackers that most efficiently get into an environment, gain privilege, get to goals, they're not the ones that execute the most commands. They're not the ones that necessarily discover the most bits of information about the environment. It's the ones that most efficiently use what they learn. So their ratio of things that they learned, distinct entities discovered or revealed as part of this versus the commands that they execute, we can correlate very strongly whether or not an environment is completely compromised, goals are met, to that ratio. So the lower the ratio, the denser the connected network is the most efficient and the highest likelihood of achieving the objectives of whatever assessment. So in the course of this examination, almost half of these engagements didn't result in domain compromise. Almost half of them petered out before actually getting anywhere good. And that correlation, that bimodal distribution, shows up in the density of knowledge versus commands executed, which is a little counterintuitive. You would think you throw everything at the wall and see what sticks would tend to get you more results, but the reality is there's a very clear dichotomy between those that use the spaghetti on the wall strategy versus the operators that are more judicious in their tool use over the course of things. So, modern Active Directory pen tests, almost a 60% co-occurrence within this in tool use. So almost every one of these engagements ends up using NSLOOKUP, Responder, NetExec, NTLM RealAX, Certify. How many years has it been since Certified Pre-Owned dropped, and we're still popping domains with ADCS exploits? It's what, 3-4 years now? Something like that. About 40% of these did reach domain admin. Certify is being used in 60% of these engagements. So these type of attacks they're the floor, not like, they're not real tradecraft at this point, I would say. So within the blue team side, concentrated auth failures. In a lot of cases, that's being modeled for, but you get a lot of noise for that. Like someone who left, there's a script running as a process that's a batch job, and now that's throwing authentication faults because the user's disabled. That kind of fun, happy scenario. LDAP object queries are really useful there. Most testers do not use a delicate approach with their Bloodhound and Sharphound, and nor do attackers. So having tooling to recognize that is very useful. ADCS, I love seeing statistics of, we prevented 11 billion attacks this quarter because we counted every single port scan that hit the exterior firewall as an attack. Port scans are kind of not great. So anywho, getting into our bits here. So the tool, it's called a Thilden. It takes those ASCII cast recordings and builds out the graphs. It produces a nice JSON structure for you to manipulate. There is hooks in there for tossing it out to the LLM of your choice via Azure AI Foundry. We use Claude via that. We also experiment with a couple others. As a side note, it can generate those nice visual attack path illustrations that everyone loves seeing in the reports and hates making. And with the right prompting, it can actually spit out the full narrative of what was done in the engagement. It takes about 2 minutes for an engagement, and 6 months ago when I did this run, it ran about 75 cents in token costs per. So it's incredibly efficient compared to humans doing the thing. So that's available on GitHub today. Please feel free to try it. I'm always happy to answer questions about the tooling and wiring it into the tmux and whatnot. So my challenge to y'all is this data set came from one consultancy. It is a fairly limited data set. Try collecting some data from your own operations and run through this and see what pops out. I would love someone to call BS on this, that this is anomalous based on the practices of one particular consultancy. I happen to think that it's probably a broader pattern of testing behavior across the universe. So, please replicate this or refute it. And with that, speak, friend, and enter. I'm here for questions. Other bits, feel free to grab the bits and pieces. And thank you for not throwing any tomatoes at me at this point. All right. Yes, sir.
One of the things that you said with, one of the main attack vectors is like if you see a lot of failed attempts from one location, how do you differentiate between like failing automation, like service users, for example, that like, what was your thinking there?
So with a failing automation from a service user, it's going to generally be limited to a particular surface, a particular resource or a particular modality. When you start seeing that multi-spectrum across a lot of different modalities, that's much more suspect than, hey, someone is running a tool, or someone forgot to change the credentials in a script, or hey, that guy that we let go 7 years ago, we finally disabled his account, and there's still, there's still a service user associated with that somewhere. So it's the breadth of the modalities as well as the breadth of the resources that are being hit is the main benchmark that I would look at that. But, all of us should have mature identity and access management and, good automation around movers, joiners, and leavers. And I'm sure that there's some people down at Mandalay that have solutions for that. But, the reality is there are zombie users that are old enough to, do all of the things on their own, that just the plumbing has to keep flowing, and it was never set up right. So, yes, sir.
So I've always had really strong opinions about standardizing hostname structure as a problem, but I've never had data to inform that opinion as to whether it actually is a functional difference between having like an obfuscated non-standard hostname structure versus having a standardized one that's easily guessable. Did you run any comparatives, or did you have an organization that you tested that had like a completely obfuscated hostname structure?
We had a mixture of both. It added, on average, 2 to 3 additional command executions to classify a host, because then we had to look at, okay, what is it doing, what is it offering, versus being able to infer, okay, FS is probably file server. DC is probably domain controller. It's the same classic argument as security through obscurity.
Sure.
But from a defensive and architecture standpoint, what you're trying to do is create more detection opportunities, and you have to weigh making it more difficult on a bad guy doing the thing versus how much pain is this causing your team who have to work with this, and they have to consult this, Rosetta Stone to figure out, okay, what the hell is Han Solo doing on our network? Versus Chewbacca, having to have that lookup table is an extra step for your team, and you have to balance the cost of providing the detection opportunity by making it more of a pain for the bad guy versus your internal. I generally don't think that the obfuscated host names really buys you anything, and it just tends to inhibit your in-house team who have to work with that. To a degree. So I don't view that as being a good defensive or detective control.
My bias heard 3 more commands from the 12, so like a 25% increase in effort potentially?
Potentially, yes.
So thank you. I appreciate it.
Yep. Anybody else? No? Awesome. Well, again, you've been great. Thank you very much for having me. Enjoy your show. Yes, sir. I will be posting them in the GitHub repository a little bit later, but if you want to shoot me an email, I can send you the data.
I appreciate it. Thank you. The slides.
Oh.
Thank you. Appreciate it. And quick question about the team logs. How did you set up the team logs? Because I'm taking the OSCP exam too. So,
Yeah, so
how did you do the scripting on the team logs?
Under the hood, Tmux allows you to chain in commands on startup.
Yes.
So we configured it so that every instance it would first launch the skinema and then pull in.
So is the program asking them all?
Yes.
Okay.
Yes. So Askinema is the playback engine and the recording engine. So normally you would run through that.
Is anybody missing their thing, or this is just extra? Okay. Thank you.
Is that good?
That looks perfect. Yep.
And we'll just have the normal controls.
I should give a small introduction about
Thank you very much.
Yeah, you can keep our intros short.
Yeah,
No
okay.
worries, we got plenty of info for people to
Okay.
check us out.
Yeah.
So,
Yeah, sure. Just 2 lines of information.
Thank you.
in terms of timing, how much time, what exact time?
So
You'll just start off when it's time, and then.
It's 11:30. I have to start it right now. You
Okay.
have until 12:15, 45 minutes of time.
Okay.
I'll inform you once the time is 30 minutes done. You still have 15 minutes, so that will take 10 minutes for the questions, and 5 minutes you can wrap up your presentation.
Okay. All right. Yeah. Sounds good.
Okay.
Yeah.
Shall I start your introduction?
Sure.
Morning everyone and welcome. Thank you for joining us for this session. Before we get started, please take a moment to silence your phones. Photos are welcome for this session. There'll be time for questions after the presentation. Our speakers today are Jenko Huang and Chris Ryan, presenting bashing cloud shells for mining, networking, exfil, and presentation persistence at scale. Please join me in welcoming Jenko Huang and Chris Ryan. The stage is yours.
All right, good morning. Thanks everyone for coming right before lunch hour. Hope to give you a good presentation here. So with all respect to Ichiro, who is quoted here, I think Las Vegas beats Kansas City in terms of heat. And in fact, the story of how we came here to talk about Cloud Shell began last year at DEF CON 33, a hot summer night, as it usually is, where we had more than 2 CTF players play a CTF challenge we built using Cloud Shell. And yes, we decided in that challenge to hide the flag in Cloud Shell. So for those of you familiar with Cloud Shells, you get a terminal on a container essentially, but it's not API enabled. And so yes, we admit, we did it just to fuck with people because no tooling could go into Cloud Shell to find the flag. So besides being not really a managed API service, Cloud Shell, in terms of the CTF, had some interesting properties. So I'm gonna not really go through the whole attack chain, but I wanna hit on a few things that informed our journey to looking at exploits in Cloud Shell. So one, you often start with API keys, right? In the cloud, that is what it is. There had to be a way to pivot to this non-API service. The way you get at Cloud Shell is in browser. How would you even do discovery, right? Clicking through the browser. AWS has Cloud Shells divided by region. There were a bunch of these things that made it fun and interesting from a CTF perspective. Players had fun. We had over 500 players. One team won. One team broke out of our root jail within the Cloud Shell. And in terms of the attack chain, really quickly, it started with an SSRF, which had nothing to do. Imagine you are playing a CTF, you're an environment, you're a pen tester, you've got API keys, there's a bunch of resources, it's a dead end for finding the flag. The key is to somehow come upon, we have to pivot, get console access, and then start looking in the Linux environments that are the Cloud Shell terminal. And where it ended up is we had to solve a bunch of technical problems to pull off the CTF. And some of those played into the last year of research. So we're giving you the history so you can appreciate the learnings, which is really much more interesting than the final end product of POC exploits and tools. So one is, in a CTF, if you have a shared environment, you don't want people stomping on each other. You don't want them to delete the flag, right? So we had to muck with permissions. We had to remove sudo, which is part of an AWS Cloud Shell. Lock down the environment, essentially. Cloud Shells reset. After a time period, that's a container, they're ephemeral, they get reset. Root file system, if you install stuff, gets reset. We had to put everything in home dir. And we had to figure out a way to hook into the login scripts to reset everything when the container and the images got reset. And of course, we had to hide the flag in non-obvious ways, even though it was in the home dir. Could you obfuscate it? And so we did a lot of things there. Which all of it led to us, Chris and I, thinking, geez, you know what would have been better is if we had an API to develop this. Who in the heck would do that? And so, of course, we decided to do it. And that began our journey. Now, Cloud Shell basics for everyone, in case you haven't played with it. It's free. You're charged if you make API calls from it, but it's otherwise a Linux shell. You got PowerShell version in Azure. There's some permissioning, some basic permissioning, depends on cloud provider, and there's some basic logging when you start these containers up, but it's halfway there. Our hypothesis back in the day after the CTF was, well, what if we could automate it? We could create these environments, maybe put stuff there, hide stuff there, use the compute, and let's see where that led. As we went on our journey, sort of the dark days of winter, well, anytime there's an API, private or otherwise, there's definitely something to attack. That's no surprise. So what we did is we sniffed the traffic, of course, but these days it's a lot easier than doing your favorite proxy capture. You can do that. You can throw an LLM at it. You can come in through the browser, do some API grabs. But we found very quickly that the architecture of all the APIs, Cloud Shell APIs across the vendors were pretty similar. You get REST APIs, you would get a WebSocket that would be your terminal session from browser to the backend container. And when we went forth and dig further, the way tokens and initial access are created is really, really obscure and is a gold mine of digging on the research side. So as an example, in AWS, of course you have console creds, but those of you who are AWS folks know you have API keys. You have different kinds, permanent, and you have temporary ones. And you have all these different variations to get temporary tokens, and that's a big thing in AWS, right? Cross-account access, assuming role. There's this get federation token call. Well, that's in the API work we did. So you have nice ways to come in and start and manage Cloud Shell environments in addition to console access. That's really key, right? Initial access is not tied to finding console credentials. And then we built in nice, pretty architecture diagram, but basically an API at the bottom and then some common services, and then we'll show you some of the tooling that was built on top of it, all in an effort to test our hypothesis. Once it's automated, we should be able to do a lot of fun stuff with it, right? And so let's start with sort of where we ended up, and then we'll go back and backfill the middle of what we learned. So here is a nice, pretty TUI. It is part of the source code we're open sourcing end of this week. We have a few more talks on this. Don't get distracted by the shiny lights. I'll tell you what's underneath. But essentially, we're just looking at a simple view of AWS nodes, 16 nodes, because in AWS, you can get a Cloud Shell per region, like a lot of resources. So one identity we've got access to happens to be permanent API keys. The API, we reverse engineered it, and we can start up a bunch of Cloud Shells per region. 16 by default, all of them are enabled. Cool. Well, the containers reset. Well, part of the protocol was heartbeat. So this heartbeats out and keeps it alive as long as possible so that after 10 minutes, it doesn't log you out. You will still hit the hard limits of the cloud providers. At 12 hours, the container will reset. But if we have credentials, we'll come back in and restart it. We'll keep it alive.
And the big kicker here at this point is that the initial API call sets up the Cloud Shell. Once this tool kicks off, we don't need to use that API anymore. That's where the stealth begins of this utility.
Now, if you think about the services, what do you get native with Cloud Shell? You log in, you can start and stop your container. You, of course, have the Linux environment. You've got a pre-installed CLI, AWS CLI, Azure, G-Cloud, and it's bound to your identity, so you can start doing admin work. You can file transfer in and out, right through the browser menu. That's sort of the functionality they give you. So all of that's in the API. Great. Now, of course, you can think you could deploy a botnet, right? All we have to do is some basic install capability, packaged agent, could be a third-party one, your C2 framework. We built in some basic capabilities so something can phone home. We've got automatic driving of the terminal session, so you can do the same things you do in browser, but a little bit more reliability. Provision, do the whole life cycle. Now, let's talk about some interesting things that come up with looking at other aspects here.
All right, Janko. So we've got our Cloud Shell botnet. But this is admin space. It was never intended to run a large compute environment, no compute intensive loads. So, who cares? An attacker would, oh no. Oh my, an attacker, he's running a crypto miner. He's running a crypto miner in our Cloud Shell. I mean, Janko, what's any good financially motivated threat actor supposed to do? Run crypto. That's what we've got here. So yes, it's a low sophistication attack. Yes, it's opportunistic, but it's possible and obviously not great in our environment, and no monitoring. As best as we can tell, this Cloud Shell has no CPU monitoring or metering dimension to it. And the classic detection mechanism for a crypto miner is compute spikes. And as we can see here, that goes right out the window.
And so we should point out publicly, Cloud Shells are marketed as free unless you make API calls and use services. But a crypto miner, of course, would not use authenticated services. It would just use the CPU of the container. So anything divided by 0 is still a pretty good number, right? So that's what becomes interesting with an unmanaged service that's sort of marketed for free. So as we went deeper, the plot definitely thickened and made us sick at times of what we found out of, so what leads us to be able to capitalize on this with a private API in those use cases? Well, we found some stuff. We will talk about AWS, but all the cloud providers have sort of a funny smell about them in terms of the design. So one thing about AWS is with the right kind of identity, you can create multiple environments. Now we saw an early version with regions. That wasn't a surprise. One identity, you can create resources that are region bound with however many regions you have access to. No surprise. Like EC2 compute instances, go to it. But those are managed services, so you'll pay for them. Cloud Shells are free. So we get 1 to 16, but now it gets even better. I have 160 nodes provisioned here, only one identity in the console. How did I get to 160 instead of 16? Well, if you look really closely, the identity column is the same user. If you look at what I federated and turned into, the second column in red, you see it changes at row 17 and 18 when I start repeating regions. What the heck is that? Basically, with one command, I can provision 160 containers that I'm not paying for in AWS because it's a feature of the way they do identities and resource provisioning. So let's talk about that. Here's the good learnings of what falls through the cracks and allows abuse. Normally, the top is what we're used to if we're AWS people. We can create resources across regions, do 16x by default, pay for it. With Cloud Shells, don't have to pay for it, 1 to 16. Guess what? When you assume a role or do a get federated call, you become another identity and you set a name that is uniquely identifying you. And that shows up in the logs. With a role, you do a role session name. It's just a little string. Usually it should be your username, but a threat actor, of course, could name it anything. If you control the call, you control your name, you control your identity. Now, is that bad? Well, in the world minus Cloud Shell, it's not bad. It shows up in the log. The use cases, an admin becomes an elevated role to do some work. Whatever they do is logged. Everything's cool. They create a bucket. It shows up in the log. We know it. But with Cloud Shell, it's unmanaged. I might see that you created something, but you can create 160, 10 for every region. Now, why does it stop at 160? There's actually a quota of 10 containers, active running containers per region in an AWS account. So AWS did not make it completely free. They put a quota on it. So our limit is 160. Now, who cares about this? Threat actors care, because you don't have to steal 160 identities to get 160 bots, right? You've got huge leverage. You need one of the right identities in AWS with the right privileges. The privileges can start Cloud Shell, can call get federation token, or assume a role that has Cloud Shell privileges. That's what we call procreation identity in terms of that. We made that up. So that's how you get big leverage. Now, I'm going to let Chris talk about our next interesting part.
Hey, thanks, Janko. So everybody out there, just a quick show of hands. How many of you have tried to debug a shell script in prod? Didn't work in prod. You had to download the script, fix it there, and then re-upload it. That ever happened to anybody? Just, yeah, every once in a while it gets us. So Cloud Shell will allow us to do that. So here we've got an innocuous looking file. It does just that. It dumps our PostgreSQL database to a file, uploads it to S3 as a backup, you know, simple, easy routine. So Cloud Shell helpfully shepherds us towards ignorant bliss by giving us a download function. Why would we distrust this? Why would we question this? Well, besides Las Vegas, I'm glad you asked. So, as you can see in their infinite wisdom, AWS has used the venerable curl command behind the scenes. When a user clicks the download button, what happens is AWS uploads the file from the Cloud Shell to an AWS-controlled S3 bucket and then clears the damned history file in the Cloud Shell. And the reason they do that is the curl command has a bunch of header files that contain credentials within them. So that means, in one of several ways, we can hijack the curl binary and manipulate content that it's pushing up to the bucket. We can even monitor for certain files, you know, like bash files that back up a database. So let's do just that. So here what we do is we specify the path that we want to download, and just like internet magic, we get our file. Basically, the browser does a GET request from the S3 bucket. That's the exact file we wanted, right? So what's going on here? Well, what we did is we overrode the curl command with a bash RC hook. Again, that's one of only several ways you can do it. And this is an unprivileged user space. So now we can read in our existing file in bash and manipulate it in any way that we see fit, including completely replacing the file if we want to. But we want to be a little more stealthy than that. And so, moreover, what we really want is our victim to actually run this thing. And all the way at the bottom, we now have a Trojanized script file. So we just added a whole ton of padding, 200 lines of padding, and we put this little line at the bottom, which will exfil any arbitrary file. In this case, it's our AWS creds to an attacker-controlled space that we want to send it to. And it'll run just as we wanted, and it'll silently execute this in the background. So we picked AWS creds here, but this will exfil any file that runs with the same privileges as this script. So classic attacker tradecraft. So there's really three versions of trust here that we need to look at. The first is the typical attack the castle. This is what AWS and Amazon are concerned about, is someone attacking their infrastructure. Kind of, but they're not really super concerned about that. The second thing is, attacking wider internet infrastructure. Sure, that's a problem, setting up C2s, that kind of thing. Maybe they'll be concerned about that. This is where things get gross. This is attacking the endpoint. This is attacking the end user. And if we can see someone in this Cloud Shell environment, they're probably an admin. So an attacker can reasonably assume that anything on that box is going to be adminning things. And again, unmonitored, largely unmonitored, largely untracked, so something to keep track of. And just a brief look, this is what that looks like behind the scenes. So this is Cloud Shell routing the hist file to dev null, so that way you can't see in the Cloud Shell history that something's happening. And as best as we can tell, this is all done by shipping around UUIDs. So there's no path checking, there's no hash checking. This is unmonitored. Everything's fine here. This is fine. So speaking of storage, let's talk about storage of a different kind, a bigger kind. About the same time Janko and I started digging into this unmonitored API calls, another researcher, Dan V, was doing some work on storage utilities throughout the Cloud Shell. So we want to give a shout out to Dan V for his great work here. Dan V's Cloud Shell store allows you to maximize your ill-begotten gains over many regions. So you go from the 1 gigabyte that your Cloud Shell gives you to many gigabytes, or in our case, across regions, 16 gigs. So why is this useful, you might ask? So think about this. This is the abstraction of digital resources. Just like the crypto mining case, this is the same resource cost blindness. It's just now with storage instead of compute. So Unlike the crypto mining case, we go from just wasted resources to now attacker-controlled infrastructure spanning victim accounts. So here we can see a 1 gigabyte file that was uploaded and chunked out across all 15 regions. So this gives you multi-region storage. It's optionally encrypted. Stolen data across multiple shards where no one region can hold the complete readable copy. And the reconstruction of this file goes across 6 to 9 regions or shards. So that also spawns many regions. So the anti-forensics on this from an attacker perspective are absolute gold. And so here we can just see, the storage per node in this case. So with all this, the victim now becomes infrastructure. The victim is no longer just a target. But this isn't just limited to one credential either. So you can accumulate multiple credentials, aggregate more storage. You can do this across clouds, not just AWS, but GCP and Azure as well. So a credential harvesting campaign feeding many compromised Cloud Shell environments can turn each victim account into basically an attacker storage mesh. So to recap, crypto mining just burns compute. This is a data confidentiality and exfil staging problem, so not just a wasted quota problem.
Third thing that gets often complicated and is critical is the handling of sessions. So normally, when we're running our private API, it doesn't matter what tool, our tool just scripts, you have in the top right a normal browser session, could be by the user, and you can connect to that same container through private API. We have 2 WebSockets. Great, awesome. We can manipulate it, we can manage it. Now, from a detection perspective, what happens if somehow in the logs we see this Cloud Shell activity? Well, we would go through typically some kind of revocation process, and AWS, right, all the cloud vendors have some way to revoke sessions, including API token sessions. So if you're doing the browser, that's the main screen, and the Cloud Shell in the browser will get knocked out. You'll lose access, and there normally would be part of your revocation cycle. However, we persist with our private API and WebSocket connection. So there is a gap. Now, I want to be clear, it's not a wide open hole because we don't have authenticated access. The container we still have access to. So the tokens that were live in the container have been revoked. But herein lies a gap, because depends on the use case, I may not need authenticated access. If I'm mining, I still get some amount of time to keep that container live. Hard resets will kick in. There is a complexity of what to do with that session to keep it alive. But it goes to show that there is often, essentially what's happening underneath is WebSockets are a different session than IAM sessions, than console sessions. So tracking those is not clean, and it leaves some cracks to exploit for persistence, depending on your use case. And it really comes down to this sort of complicated picture of IAM within AWS, all the different sessions, all the API keys and credentials, and how you get from one to the other. And so this is probably a different sort of dive deep research topic, but the point is the bottom left is what opens the crack. Once we have a WebSocket open with our terminal, the revocation procedures don't work immediately. We have to wait for this 12-hour container reset before we lose access. Now, AWS is aware of that, reported it, but it's downgraded to low and informational because IAM access has been revoked, right? But that's a very, very biased view of the world. It means your main castle is all you care about. Unauthenticated, you don't. It is the consumer version of I've hijacked your printers or your Wi-Fi router sitting on the internet, and I'm attacking others. I'm doing stuff, but you don't care because I'm not in your home, right? This is the stuff we deal with security-wise, and we see it here as well. And generally, we've been talking a lot about AWS, but all the other cloud providers have similar and different issues, right? This is not an AWS issue. It's IAM is hard. And so as an example, one of the things that's apparent from the reverse engineering of Microsoft's Cloud Shell API is that you can do a device code fish and then turn it into the right token to get Cloud Shell access. And that's a big thing because if you're in Azure land, that's been a big topic the past year. Storm 2372 last year, Russian threat actors, hijacking PRTs, but also playing with device code phishing. Evil tokens, phishing as a service, a couple months ago, incorporated device code phishing. This has been talked about for 5 or 6 years, including at DEF CON 29 when I was here last speaking. So it is big because the user will authenticate and authorize some app that's either being phished, go through MFA, and this flow is the device code phish flow, and the attacker gets a refresh token and an access token. And they can, of course, do a lot of damage, but they can also, with the right apps, they can do Cloud Shell abuse. And so this is joining 2 major attack vectors. This just means initial access is a lot easier in Azure than probably the other providers, right? Because device code phishing is highly effective. It's being used in the wild. There's a lot of scripts. It's a no-brainer. And really, this is the detailed protocol flow. What's in the red box is the key to joining a device code phish on the front to get the right token, to flip it with the right perms to do Cloud Shell abuse. And the other problem with Azure is the IAM is a mess, the logging's a mess. We know it because they've have decades of products and customers, but there's no explicit Cloud Shell permissions. It is really hard to know what Cloud Shell activity is being done. Versus AWS has at least Cloud Shell private ones, but they show up in the logs. What does start Cloud Shell mean in Azure? Good luck. Is it in the Graph API? Is it in some other? Good luck. So that is part of what came of the research.
Thanks, Jenko. In addition to AWS and Azure, we haven't left GCP out in the cold either. So another initial access method is a free Gmail account. They're out there everywhere. It's really easy to sign up for Gmail. And when you get a free Gmail account, you can get into a Cloud Shell. So a person can register for that free Gmail account, which is super common, and then go to shell.cloud.google.com, and you can get in there. So again, an attacker can benefit from IP address reputation laundering, particularly in the Google IP space. So this is more abuse infrastructure. We can link it to existing tooling, just like before. We can add it to the crypto mining net that we have. We can add it to our storage botnet, et cetera, et cetera. We can run a C2 from up in there. So this particular one is an area of further and active research for us, and hopefully we'll have some more to share with you shortly on that.
Part of that story is what's some of the biggest attack surface in the world? Gmail. It's probably got to be one of the most popular apps in the world, period. And it also pulls personal consumer. And when they market it as a free service, it's one cloud, one identity. They made it easier, so it's not like enterprise provisioning where I have to enable Cloud Shell for my employee. The personal use case makes it easier for the attacker to abuse with a huge attack surface. So that is one of the big things on the Google side. So maybe to summarize what is really important out of all of this, it's not exactly each of the use cases or the tooling showing that. You can think of more. It is partly understanding how they come up, because if you're researching it, that's where you're going to find more cases. If you're defending and you're blue hat, you're going to have to think about it from why did this occur? These aren't CVEs. They're more like design quirks, multiple ones intersecting, and vendors, if you're producing it, the only hope is you better design up front before you roll stuff out. So I will have some catchphrases that I think capture why we're here. And it's very hard for people to take these seriously. I think the first 2 are still things that people do by default. They think just because something doesn't have an API, It's sort of safe from all the API mess we've been dealing with for 10 or 15 years. They also think temporary is secure. You hear that all the time. You have a temporary bloody token. Well, at least the duration's only 15 minutes. And that you see in public remediation guidance in documentation from all the vendors. It's like, yeah, just wait for it to expire. Contain it, wait for it to expire. Part of that allows us to exploit Cloud Shell abuse. The next three in the middle are more implementation design things. And of course, they're never by intent, but it's just what we get with. Like, no one wants to do half-assed stuff, but we know security's second fiddle in every company. So if you're rolling out stuff, we get half-assed IAM permissioning, we get half-assed logging. We absolutely do. I'm not saying we get zero, we get a little. And a little is not enough. And so that's like a safe with a cardboard back, in my mind. Complex auth token flows, sometimes you can't avoid it. It's how do you go from a console login to an API token? How do you go from SSO SAML to a OAuth refresh token? It's all over the place. And that's exactly what was exploited in the Cloud Shell abuse. We have a bunch of different ways to come in and different users and credential types. Separate multiple sessions, yeah, we know it. We pointed out there's a bit of a hole for additional access. But the revocation's got to look at it as one unified session somehow, and it's not. The last three come back to a bunch of biases that often are implicit, but I just think keep being done. We look inward because that's where our resources are, but part of the resource is the container, even if it's not making API calls. People don't care if you don't have to pay for someone using your resources to go attack someone, then you will you won't care. That's what we have with Cloud Shell. What about the user's endpoint? Chris showed malware injection. Are you expecting your own Cloud Shell, which runs inside your IAM, to deliver you malware? It's not even on your list. And if it were on your list, it's at the bottom, guarantee it. It's not on your list because it's not a managed service. There are no practices for securing Cloud Shell, right? All of these bias us. The shared responsibility model, AWS pushes it, but every vendor tries to say, hey, not my problem. We're the infra, you're the guys who got fished. It's your problem. Yeah, in that is a huge divide. Divided attention. This case is customer doesn't care, they don't pay for the Cloud Shell. AWS probably has it in their cost model, so unless something makes that needle go, they will never look at a compromised abuse with a customer. They won't. Who cares? You guys change your passwords. Do what you're supposed to do. Put in MFA. So that divided model means this is, again, low on the list. Who cares about Cloud Shell attacking the internet with bots? Who cares about it hacking back? All of these, how do you even describe this to talk with people, vendors, yourselves? We don't even have the right terminology to talk about this design interaction kind of holes in abuse. In terms of where we need to look to summarize, these are the three hot areas. Again, defending, attacking, that make a difference. It applies to most cloud stuff. If there's a protocol involved, obviously you want to look deep there. We found a bunch of things that just smelled funny. AWS file transfers, 2 hops through a public bucket owned by AWS. Ooh, that's interesting, right? IAM is the key to almost everything in the cloud. The perms, not just the perms, the tokens, the auth flow, and of course, in this case, the key resource is the container. Can you keep persistent access? Can you abuse it? What does that mean, right? There are quotas, on it. That's important. So maybe to come in and sort of wrap, what are the takeaways depending on your perspective on security, your day job? Well, I think of it as a couple things. Red team, research, the areas that we touched on, these will reap things, but I suggest the bottom 2 are where people aren't looking. People ignore persistence. If you're willing to go low and slow, there's a bunch of abuse that won't get addressed. We know it with APTs. They just hang out. They're very stealthy. We think about initial ask as priv-esc and data exfil. 2 directions are ignored out of 3. What are the 3? The main one everyone knows is attack the castle, all the goods. The second one people are aware of is attack the internet and bystanders, because we do know about botnets. The third one is attack back to the customer, but their edge. It's the client, the admin on their endpoint connecting, and we're right at the perimeter. We're not attacking in, we're delivering malware. We want to get to your endpoint, and that's our pivot in lateral discovery. It's not inside, it's that way. If you stick there, everyone's far behind. Blue, boil it down if you're SecOps or admin, how about no Cloud Shell? You can't turn it off. How about managing it? Maybe you think you can keep it under control. It's a little bit dubious, but maybe you use this private API to do it. Build your own. Screw it. I'm just going to set up containers. It's been done. If you got some develop time, set up your own containers, allow a connection, do whatever you need to do for your admins. Hey, maybe you can turn it like Dan V into some slush storage and compute. Maybe you can be a profit center, mine a little Bitcoin on the side. That's a little bit of a joke, but part of it is think about leveraging it instead of throwing it out the door and locking the door. Use cases, you got to think about all three attack vectors, right? Vendors, if there's any vendors who are gracing us with their presence, nothing's for free. It isn't. It's just who pays for it. We all know that, but stop doing it to us. Never roll out half-assed shit. Please make it a first-class managed service, because someone's going to abuse it. One session, don't break it into pieces, don't expose that to the world. People will pick at the parts of a session. Design and think about the interaction of all these pieces from all these use cases from the attacker perspective. It's sort of obvious, but then we have this, so it's not really been done enough prior to rolling out things. Every little group is acting independently, it seems, at vendors. So that's sort of my wish list. Maybe a little bit of hope in there for others, but in the end, this is what we deal with security-wise. And so really, maybe to wrap it up and allow some time for questions, if we do have some time, do want to make a few notes, though. AI is a thing, obviously. We used it in some of the reverse engineering up front, saved some hours. The tooling we built saved a bunch of hours. Is it dangerous of sloppy code? Absolutely. So if you ever download the stuff, don't trust it. This isn't going into production in my area. Usual things apply. But the bar to abuse this stuff with AI obviously is low. There's script researchers, script kiddies, script developers. And it's shockingly low what the big LLM vendors have scraped and put into their models, including stuff around things that haven't been productized. So, in a way, there's a bit of an Oppenheimer moment of ethically, I'm sort of mapping it to nuclear fission and back in the days of World War II. Our work as researchers, talking here, we have to think about, is this going to end up used badly and maliciously, or is it going to help us increase security? And I'll tell you, it's not clear, right? Who's going to scrape this first? Which leads into our point. We will be releasing end of the week, after we get through other talks, on that repo, all the code, the protocol wrapping, the POC tools. There will be a no training model. Source code will be there for research. I don't care who you are, go to it. I know people will ignore it. I want people to explicitly acknowledge their scraping stuff and dumping it into their models if you're from one of the big vendors. Because I think that's where we are as an industry, trying to think through those things. Thanks for coming. Love to take a few questions if you have it. Otherwise, catch us around or follow up with us, and just love to have conversations about security.
Great presentation. Is this turned on? Testing.
You can shout and we'll repeat it.
All right, I think it's on. Great presentation. Thank you very much. It delved into a lot of things that I had questions about when I saw my people using Cloud Shell, and I was like, that could be abused. You guys proved it. So one question you said, so coming from an Azure point of view, I know a lot of this stuff. Can you turn off Cloud Shell? Because I haven't figured out how to do that.
So ongoing research, but what to date on Azure, the question was about Azure, can you turn it off? Great question. There are some permissions for persistence, which is really the useful version of all these Cloud Shells. Azure does one thing right. It makes the persistent storage a storage account. So it's now, the storage is now managed and visible. So you need permissions on that. So you could control at storage level at least persistent Cloud Shells, which takes away a lot of the good, bad stuff done by threat actors. Ephemeral containers, you will temporarily install stuff. Azure doesn't allow root. A second good thing they did, the other two do, GCP. So start with storage accounts. There's also a read on the subscription, but most of your users will have that. So you can look at those two intersections as a starting point to lock down Cloud Shell.
So is this a special storage account that backs the Cloud Shell?
So at provisioning time, when you do it manually, or if you automated it, you can choose a storage account when you provision a Cloud Shell for a user. And by the way, it's one-to-one environments, so you don't have this old nasty creation of many, many environments, because once those environments are created, it's really hard to find them in AWS. It's really hard to find. You have to log in as the identity and go find it, and you have no, you don't know what, you can look in the logs, but it's really, really sketchy. So you've got a fighting chance. The thing working against is it's not a clean permission. It's not Cloud Shell, and you have to reconstruct it, which is their implementation, which often comes up in Azure. So, but they've done some things right. No root, there's an explicit storage account, and you can start there of making sure, lock it down, or provision, only allow an admin to provision, not a self-provision.
Thank you.
I think we got about 3 minutes. Any other questions? Otherwise, welcome you. Appreciate you taking time. Come see us, and if there's any follow-up, drop a line. Again, love to talk security, Cloud Shell, and other cloud. Both Chris and I, and thanks again.
I'm just going to make one quick announcement, and then we'll listen to our speaker. I'm just reminding you all of the photo policy. Please don't take any photos, especially with other people in them. If you can get the slide, that's fine. Enjoy the talk.
Cool. Oh, thank you very much. We got technically a minute to start, but I also have like 80 slides, so and a Red Bull, so might as well jump in. Howdy, folks. My name is H.D. Moore, co-founder of Run Zero. Prior to that, folks probably know you've been working at Metasploit for many years. One thing I like to do a lot is kind of like my fun times is like exploring networks, like finding things you're not supposed to get to. And so this is really kind of like one aspect of doing that. So if you've ever done like identity attack path mapping through tools like Bloodhound, for example, it's kind of like doing that, but then doing that for network devices, networks, multi-protocol gateways, and things like out-of-band management systems. So kind of taking that like identity graph mapping model and then kind of turning it on its head a little bit and trying to look at it through the lens of network access, out-of-band management devices like BMC, serial console servers, things like that, as well as like OT protocol backplanes like Modbus, Ethernet SIP, IP. So hopefully a kind of fun way to turn the topic upside down a little bit and also provide some practical tools for playing with this stuff, of course, in your own network and in your own company. So, when you get into security or get into computing, you always think of networks as being these big, beautiful, perfectly cabled things where everything is, every cable is in the right spot. As my wife likes to tell me, these are like unreasonable internet beauty standards for cabling. My rack does not look like that. But once you get into the field, of course, things look a little different, right? Like this is really what my first job looked like, was a telco in San Antonio, and there's probably a possum or two in there. There's water over the floor. Things were bolted to the wall and plywood. We had no idea how anything was cabled, right? Just giant rat's nest of cables with no idea where what was where. But as long as no one complained, it was fine. That was kind of our view of the world. Is like, well, as long as phone calls are coming in and everyone's getting their data, it doesn't really matter. It worked. It worked a little bit longer at least. Now, when you get into like more of the network map, you have a similar model. Like if you've taken a job in security and gone to an organization, one of the very first things you typically ask for is a map of the network. Like, what does my environment look like? How is it connected? Where are sites? Do we have site-to-site VPNs? And you may get this like beautiful diagram that's in like 6-point font that apparently is a masterpiece built by a cabal of network operators who only meet on Saturdays at midnight. So there's definitely some ceremony around this stuff where folks build these like really nice, redundant, multi-leg flows. But reality is this thing, by the time it was even finished, it was already wrong. As soon as you have your first kind of like, well, I'm in a hurry, I need to cross a cable, or this is broken, or someone's plugging something in really quickly, it starts degrading almost instantly. So almost by example, there's no such thing as an accurate network map. Things just move so often. And there's a million different examples that I'll cover some of them as we get into it. But this talk is really about like, how do you find all these like broken misconnections? How do you take this like hot mess of constant change in our environments and use that from an offense and defense perspective? So the mistakes that you see in these things are often really subtle, and they're subtle because no one notices it, right? One of my favorite ones recently was a customer got mad at me because we told them their system was exposed to the internet. And that system in particular was their Suricata box. It was doing all the network monitoring, it had full span ports. And we're saying, hey, this thing's not on the internet, you should take it down. And he's like, this is my span port box. Of course it's not on the internet. Like, it's a span port coming in. Well, ends up, he connected it to the outside line of his Comcast connector for the business, and they gave him a routable IPv6 address. And so their most important data tap of the entire company was sitting on a raw IPv6 address reachable by anybody. And it's things like that we just don't notice it. The only reason that happened is because even though there wasn't a static IPv4 setup, of course, if you're on a V6 on a link with a V6 router advertiser, you'll just get a V6 global unicast address and start getting routed traffic. So even somebody who's like very security minded, who had done all the right things of turning off the IP addresses, thought they had their interface locked down, was still effectively putting their most secure system on the internet without knowing it. Another example where this runs into like really common is when you have a statically addressed VLAN, like every IP in this network is a static IP, but then someone crosses wires and connects that to another totally different VLAN. And so you end up having like two networks kind of on top of each other. So you'll see ARP traffic for both different segments. An example of this is the customer of ours in Australia who found like that the building access control, the building management system VLAN was on top of the guest wireless, and no one had noticed for like 3 years. Because the building stuff worked and the guest stuff worked, and no one really knew the difference between the two of them. And the challenge, of course, is like, all it takes is the attacker being like, hey, wait a minute, like I can turn the doors, I can open and close the doors from here, or I can turn all the HVAC off, things like that. So it's really easy to go from like a really small, subtle misconfiguration to a huge exposure you don't find out until it's too late. And I guess the longer it goes on, the worse it gets because you don't realize how who else has already found it, things like that, until you get there. So this happens very similarly with identity attack graphs. Like if you've got this beautiful Active Directory forest or this Entra ID model, you've done everything you possibly can to reduce privileges and lock things down, and then someone's in a hurry and has to add someone to a group last minute, right? All that goes out the window. You immediately have like one of those shortcuts between two parts of your graph where everything you've done up to that point to really secure your environment has now fallen apart because of a really quick mistake. And of course, unless you're continuously testing that stuff, you're not going to find it. And there's very few people who continuously test that. So the challenge with all these things is the more complicated the network is, the more stuff you put into it, the more likely that a small mistake will compound to a big mistake. So this kind of gets into like, well, why are we talking about this in the first place? Well, segmentation is our band-aid for everything. Like, if you can't secure it, you can't patch it, it's third party, it's whatever, you stick it in a segment someplace else. You say, okay, I don't trust this thing, let me put it in its own little box over in the corner, and we're gonna leave it alone. The challenge, of course, is like you put everything to its own little box at some point, and oftentimes you're putting them all into the same box, and they can talk to each other in the same box. So you're almost, in some cases, putting all your worst stuff together to play with each other, and that's not necessarily good. So this is an example of like one of the NIST SB 800 publications for a guide to operational security. You see they've got like these very clear delineations between the DMZs, the different layers. They've got a firewall between every single segment, things like that. That all looks nice and clean and beautiful. This is another example. It's a little bit different. So instead of having like your physical segmentation, like that OT graph there, this is the PCI DSS diagram for how you segment your data. One thing I like about this, even though this document is 10 years old, is they have this like little red box around this admin workstation in the corner. And the reason they do that is they're saying this is a security impacting system, therefore it is in scope for PCI. So what that means is even if it's not processing credit card data at all, if that machine can log into a system that's processing credit card data, it's kind of like by GVL, if you will, by virality, it's now responsible for that system. I've ran into one of my favorite pen tests was a recurring pen test. We did the same customer every quarter, a giant merchant bank, like 12 million credit card numbers all stored in a big database someplace. And the goal was always go from outside to the credit card databases and change someone's credit. Just make their balance go up and down, right? That's actually really where the store of the balance was. So you could literally give people more or less money. And of course, like every quarter we won, and every quarter it got harder, and every quarter things kept changing on us. So one of the tests I got to work on that was really fun is like, okay, everything is like super isolated. They've got CDE, non-CDE, so card data whole environment. How do you get from one to the other? And so some of the techniques we're going to talk about are how we found that initial pivot point. So the NetBIOS technique here is actually how we found this. But in this case, it was the SolarWinds Orion box. Before I ever knew that SolarWinds was owned, this is pre-Russian discovery, I guess. SolarWinds is expensive as a product, and they didn't want to buy two licenses. So instead of having one version for the card data hold environment and one version for IT, they just had one box. And that one box had one license on it, and it connected to both CD and non-CD. Now, unfortunately, if you know what SolarWinds Orion is, that's terrifying, because SolarWinds has all of your passwords to all of your network equipment. So everything that creates the segmentation of your network lives in those passwords on that machine, encrypted to a local DP API key you can rip out of memory. So I was working at Atreides at the time. We published a little script for ripping out the DP API key, decrypting all your credentials, and we basically use that to basically steal the passwords for all the Cisco ASAs. And instead of having to like do anything at all in the card data hold environment, we just cut a hole in the firewall to let ourselves through. Like your segmentation doesn't matter if your attacker owns your segmentation process. And that could be your firewall, that could be your layer 2 switch, that could be anything involved with actually enforcing that segmentation is actually more important than necessarily than almost anything else you're doing. Because all it takes is for someone to like, add another VLAN to a port and all your segmentation goes out the window. So separation for this stuff goes beyond cabling. It goes into like more of the logical aspect of can X talk to Y and so on. And that's where a lot of the Bloodhound graph stuff comes into place too. It's like, can I get a shell in the system? Can that scrape a session out of memory? With some of the new Bloodhound Open Graph stuff, you can then use that to chain into things like 1Password, GitHub, Azure, all kinds of fun stuff. So taking a little bit further, here's an example. I like to pick on Fortinet for obvious reasons. We all get to hear about Fortinet in the news every week or two. And they have these wonderful diagrams about how they secure ICS security. And they have these things like, okay, here's level 5, level 4, level 3, all the different OT layers. The NIST 800 document talk about how firewalls are basically the primary mechanism for enforcing segmentation in OT. Like, we all know that. The firewall is doing all the job. Now, what a lot of folks don't necessarily realize, it's all the same firewall doing all these jobs at once. And it's also the same firewall that typically has a new remote access exploit every month or two. That has to be publicly accessible for you to be able to get to the VPN in the first place. So by definition, all your eggs are in one basket, and they're directly exposed to the internet, and there's a long recurring history of serious vulnerabilities in these products. And I can pick on Fortinet here, but you can also pick on Palo Alto, Cisco, anybody else. Like, these kind of edge devices have been in the news for years for a reason. They just keep getting popped, and they're typically getting compromised through exploits that were not known to the vendor at the time. So by the time the vendor puts out an advisory, you're hearing about the IOC and maybe not even the patch. You're not even hearing about what to do about it. So if you start getting to bigger networks, this is more kind of a logical breakdown. So you may have a DMZ, a corporate net, an IoT net, wireless. Then you have your factory OT, whatever it happens to be, and then your OT firewall, then all your stuff inside of it. So just giving a sense of how the network is roughly shaped. And the idea is, how do we find leaks? How do we be able to go from, let's say, the wireless to the IoT, or the IoT to the factory, or one layer of the factory, like maybe the level 3.5 DMZ, into the supervisory layer, all the way down to the process layer? So there's 3 techniques I like to use for this stuff. One is identify network bridges. So any device that can is connected to more than one thing at once, that is a bridge. That's a router. Whether it wants to be a router or not, you can make it your router. So we'll talk about how to make things your router and how to basically use any multi-home machine as your router. I like finding cross-protocol gateways. So if you're familiar with web attacks, relaying an HTTP request, it's like that except for not HTTP. For example, you can relay a TCP/IP connection into a serial port bus connection to another TCP/IP, back to another serial bus again. You can do some pretty wild stuff in the protocol layers. So we'll talk about that. And lastly, out-of-band management devices, which are a lot of fun, and we're going to be dropping so much zero-day on this DEF CON and Black Hat in the next couple of days. So I'll touch on that a little bit here as well, but those are a lot of fun. So starting off with bridges. So anything that has more than one network card at a time or multiple interfaces can be a bridge. By definition, it's got 2 things. Data comes on one side and come out the other. And it's not necessarily configured as a router, but if someone can break into that machine, obviously they can go from point A to point B. And they may not even have to break into it to get their traffic to go through it. So a really good example of that, you can have a laptop like this where connected to the wireless, and let's say I'm working for some sort of manufacturing area. I go and I bring my laptop into the OT environment. I plug the Ethernet port into my dongle. I'm doing my thing, whatever, it's all fine. But I did not turn off my Wi-Fi adapter. My Wi-Fi is still connected to the guest wireless of the organization. So technically, I'm now the router. I've now created an access point to the guest wireless network into the OT environment through my laptop right then and there. And that seems a little bit obscure, that's not a thing that would actually happen. However, what's running on your laptop? If I'm running Docker Desktop, for example, the very first thing Docker Desktop does is turn on IP forwarding with no firewall rules. So any network interface going into your laptop at that point, your device is now routing by default. And people don't think about their laptops being these kind of temporary gateways, but they're often the easiest, most reliable way to go from point A to point B is to bounce through someone's workstation, especially an admin workstation as they're walking around. And if you talk about, so if every device with more than one network interface is a router, nearly everything is a router. Because if you look at, if you had a Mac OS machine and you type ifconfig right now, you'll see 28 different interfaces on a brand new machine. That's everything from the wireless display link stuff to your Bluetooth stuff. There's a million different things, tap adapters. And if you just connect a local Ethernet segment, you'll get a ton of IPs. You'll get your V6 IP, you may get a second V6 IP, you may get a V4. And so what's interesting about this is so many of these devices are multi-homed, and very many of these devices have IP forwarding turned on by default. So a lot of your home printers, they all have a Wi-Fi card and an Ethernet port and a Bluetooth PAN network, and they also have IP forwarding turned on by default for who knows what reason. So you can literally go into one side of a printer, set your route, and route through the printer. And that's it. That's the entire thing. There's nothing you had to change or set or anything. There's no hack involved. You just basically treat your printer like a router and it routes. That same type of attack works for so much stuff, whether it's point of sale, access control, building automation, just devices for some reason like turning IP forwarding on. And there's many, many different ways it happens, right? So you've got, when you're migrating a server and you get a backup link, when you're using hypervisor, you got all kinds of virtual stuff. You've got engineering workstations that are moving around. You've got tethers, you've got mobile tethering, you got a cellular gateway, vendor managed appliances. Just all these things end up adding secondary interfaces. And you find IP forwarding off by default on most Linux machines, but then that gets turned on by so much stuff. So container runtimes, for example, Lima or Docker Desktop. Anytime you turn on hypervisor networking, for example, it has to turn on IP forwarding for that to work. These are kind of kernel level settings. If you turn on tail-scale subnet routers, very first thing you turn on IP forwarding. If you type WireGuard and you post up, that turns on IP forwarding. So all the stuff you typically do just to use your computer is actually also turning your computer into a router. So talk about the printer example real quick. Basically, you can go from point A to point B, pretty straightforward. And if you're able to exploit the printer, even better, but typically you can just route through the thing without having to exploit it. Vendor tunnels are always terrifying because you'll have a device that's inside of an important network that's beaconing out through the internet or beaconing out through an LTE card, and who knows where it's landing. Like some of the recent water utility hacks we saw were because the water utilities device was exposed on a cellular network that of course you don't have the IP range for. You're on the cellular's random network. You don't even know where you're going to roam to. So you might be on a private APN, but oftentimes you're not. So you'll have a random Digi International router on a random IP range tied to Sprint or Verizon or T-Mobile, and you have no idea that it has anything to do with your utility or your business until it's too late. So it's really difficult to find those things, especially from the outside. But you can find them from the inside through different techniques. So how do you go about actually finding these bridges? So you can actually ask the system to tell you about its IP addresses. You can try to correlate its unique identity across multiple places, or you can forcibly shove packets into it and see how it errors back, right? So a fun technique a lot of folks don't realize, you can do NetBIOS, like NetBIOS name lookup. You query an IP, you get the name. There's a second thing you can do. Once you have the name, you query that name from the system, it'll give you all its IP addresses. So it's not really common that folks realize that as long as it's running the NetBIOS name service, you can get it to list all of its IPv4 addresses, including ones you don't necessarily know about. So a really quick way to get your secondary IPs. SNMP, if it's got v2 open, of course, that's easy. You can not just dump SNMP from the device itself, but you can go find the printer on the same network as the device you want and dump its ARP cache and use that to find information about the asset. This is probably my favorite technique just because it still works with modern Windows. The DCRPC Oxy2 resolver, this is like a super obscure thing that got put into the Impacket source code like 10 years ago and no one really thought about it. But what it does is you can ask it for the system's IP address and name, which doesn't mean a lot, except for that it'll actually give you every IP address, including IPv6 addresses that nothing else will do. So unauthenticated remote list of v6 and v4 addresses of every device running Windows. So if somebody's running, let's say, like a NordVPN or whatever sketchy VPN tunneling software, you can actually find those VPN tunnel IPs coming back in DCRPC response. So you can literally scan your local network, find out all your employees who have a VPN adapter of a different network without doing anything else, no authentication. So it's really, really useful for finding folks that have extra links you don't know about. It also ends up finding your LTE mobile tethering links as well. So the other way to do it is you find a unique identifier for an asset, and then you try to find that same unique identifier in multiple places. So a really easy one would be SH host key. Obviously, there's firmware that are hard-coded, but if you see the same key on more than one IP, it's probably the same device on more than one network. And if it's on more than one network, by definition, it's a bridge. So just the kind of logical setting there is if you can uniquely say this device is also that device, then these two devices are connected together, it's bridging those two networks, and therefore you can tune that to a pivot point. And there's a bunch of ways you can do that. You can use TLS certs. SNMP v3 has a pre-auth identity leak that's really good. End-to-end SSP hostname links to RDP, SNMP, et cetera. Let's see. SH host keys, of course. But there's basically anything unique you can leak out of a system you can use. Even the SMB protocol has a SMB2 GUID value that's a random Windows GUID, but it changes every boot. And so if you touch the same machine on two different IPs and it has the same GUID and that's all you see, you also know it's the same machine. So there are lots of ways to kind of do these out-of-band confirmations that the device is the same device. And then finally, we'll talk about protocol gateways. These are things that are not necessarily IP addresses, but they get you access to lots of stuff behind a gateway. So in this case, we've got a HVAC building management system over in the corner, and it actually has the ability to talk directly to an RTU inside the factory. So for example, this could be a fire suppression system. You could have a thermostat system that's wired up as a backnet gateway. It could also, through the backnet bus, be talking to all your other equipment, including your fire suppression, control, safety, sprinklers, things like that. So what's neat about this is you can go from an IP network, which we all know and love, to a random serial port network that we know nothing about, and then talk to random serial devices. Now the wild thing about this is you're actually sending serial packets on like a 9600 baud bus. So if you spray packets at this poor device, it's just going to be sending really slow, super slow 9600 baud line rate on the back end. So you can overload these devices really, really easily just by asking them too many questions really quick. But you can find these different protocols through local broadcasts, like OPC UA, through Unicache, by spraying packets, looking for it, and also for packets like KNXNet, you connect to it and subscribe. Backnet's one of my favorite, though, just because there's so much stuff. You connect to a backnet gateway, which could be like a little dinky thermostat that doesn't look particularly important. You register yourself as a foreign router for it, and then you start actually enumerating all the space through broadcast. You could find every single device that device knows about, even the chain of connections through backnet. And it's a really neat protocol. I believe ZMAP now has support for it, as well as Nerva. The really cool thing about backnet is a device that you may not think anything of could have 1,000 other devices sitting behind it. So this is a really quick example of that real quick. This is an example. We did a scan of all IP4, Ethernet IP, and backnet devices across the internet. We found out 6,000 routers, and of those 6,000 routers, we found 102,000 devices behind them. So it's like a 20x ratio of backnet devices to devices behind them. And there's scary stuff out there, right? You can type in Armory or whatever. You can go find someone's random munitions dump. and you can go into like mechanics room, see the devices, the firmware, the version, all that kind of fun stuff. So you can get pretty deep. You can even tell like whether the device is faulting. So this isn't just read-only. Like if you can talk to BACnet through this internet-exposed thermostat, you can trigger the fire safety system. You can turn off the lights in the bathroom of the canteen. You can do whatever you want here. So this is full-on watchdog style takeover fun network stuff, which is amazing. And folks don't realize it because when they scan the local network, all they see is a thermostat. But if you're able to enumerate through BACnet, then you find everything else behind it, which is way more important. Strangely enough, this is really important for schools. Schools have a lot of HVAC equipment, safety, fire, alarm, drill stuff, and they're typically all connected to one or two Ethernet exposed BACnet controllers. And at that point, you can then do horrible things, right? So this is what a BACnet controller looks like. If you do this type of correlation and throw it into Bloodhound, you can actually see the relationship of BACnet device to controllers and stuff. So with Ethernet SIP, this is also a really fun protocol. It's probably my second favorite protocol in the OT space. It's called Ethernet IP, which is dumb because it's neither. It's just a UDP traffic over, that you can then tunnel other things on top of. But it's neat in that you can talk to multiple transports. You can do Ethernet SIP, Ethernet IP to enumerate all the devices on that particular system, like listed identity. But then you can also make connections through that device to other devices. So anything that's reachable through Ethernet SIP, or Ethernet IP, including like a serial device, you can connect to by bouncing through the first Ethernet IP device you find. What's really neat about Ethernet IP, though, is you can keep chaining it. So you can connect to a serial device that talks to a TCP IP device that connects to a serial device again, and you can go multiple hops around the world in that sense that way. One of my hobbies as a teenager is we try to use out dials to go around the world by dialing people's modems. So you dial into one modem, log into it, then dial another modem, keep doing that through out dials to see how long around the world you can go, and then try to like type a command on a shell and see how many seconds it took for the character to show up. So it's kind of like that, like just trying to see how many chains of proxies you can do. But in this case, instead of proxying stuff, we're doing TCP IP over serial, over TCP IP, over another bus, over serial again. This is never do this, but because Ethernet IP allows you to target an IPv4 address as a destination, you can turn every Ethernet IP, crunchy old OT gateway into a port scanner and a like remote ping system. You can basically start spraying packets out on the TCP IP side through an Ethernet SIP device, even if it's like going through a serial network in between. So you can go like IP address to a serial bus network to another Ethernet SIP device, and then make that start port scanning the internal network for you. And of course, you're more than likely going to kill the whole bus at that point because it's 9600 baud, but you can do some really wild stuff on that front. So example of that, of just that stuff. So Ethernet SIP is great. This is also widely targeted recently by especially the Iranian hackers because it's all over the internet. All your Allen Bradley, Rockwell stuff speaks this stuff, and you can break equipment really quick. Modbus is a fun one. Has anyone here worked with Modbus as a protocol? Awesome. So in a normal world, you say, here's a protocol, it has a discovery function, it'll tell me where the device is. Modbus is not that. Modbus is like 20 years of garbage all stacked on top of each other. So the way that one vendor will let you identify the device is to write a certain set of registers, and the way that another vendor will do it is you call a function call. But every vendor is a little different. Some vendors don't support function call 43, some of them don't support any function calls, some of them have the ability to give you a device identity, but only if you write to a certain register. But that register may be used by a totally different device someplace else. So there's a story I heard recently about a particular large vuln scanning vendor that burnt down a cookie factory because they were using the device identification sequence to write to a register, but the systems they were scanning were not that vendor at all. It was a different vendor, and that vendor, that was the temperature setting for the oven. So you wrote the register, it just like burnt down the whole thing at once. So that was a very bad day for everybody, and no one got their cookies. But that's an example of like where it fails at scale. Like you can literally burn down a factory by just touching the wrong registers with Modbus. And so here's an example of using Bloodhound again to then map Modbus back to devices. The graphs all kind of look the same, but you kind of get the idea. We're using a TCP port 502 to then find all the downstream Modbus units. KNXNet's a really fun one. So while BACnet is really popular in the United States, KNXNet is the one really popular in Europe. And that has an interesting property in that it's not like BACnet where you get to see it all right away. You can connect to it and you can register for stuff, but then you have to listen for background traffic. So you basically have to like slowly get a list of all the devices that are talking after just seeing them speak for a while. So you can connect to it, but then you have to like hang out there for an hour or two to get a list of all the devices, then you can start digging into it. Let's see, so yeah, the stats I showed a minute ago of 6,600 internet-facing BACnet Ethernet IP devices across 100 countries, like almost 102,000 devices were behind them. And I can tell you that for like some of our large school system customers, they find one device and has like 1,200 devices behind that one device. And so they're like, hey, it's a thermostat, I don't care about it. And they like realize, oh, we can actually do our anti-shooting drill lockdown stuff. It's all triggered from the same system because it's all through the BACnet protocol. If you want to play around with a little demo I had up there a second ago, HTM.io, data, ICS, HTML. That's if you want to go play around the map. It's slightly censored on the IP side, but it's all real data. So getting onto the fun part here, I know we're short on time. Out-of-band access devices. So these are my favorite things in the world because they're all terrible, and they let you completely go around all the security of the device. So you could have the best security in the world, you could lock down your server, run everything you can possibly do, and yet your BMC, your KVM, your serial port server, even your PDU can hijack and take it over anyways. So these devices let you basically bounce between almost any layer, because oftentimes you'll have the BMCs will be on their own network, and then once you compromise the BMC, you can compromise the host BMC. Yeah, so just starting from like IP KVMs. So these are fun examples. They provide USB devices, a video controller, some present a USB NIC as well, and they're all kind of below the host boundary. So it's like you're sitting on the keyboard, typing stuff in. So these allow you to present, not just the keyboard and mouse, but full-on mass storage. You can mount a drive, you can reboot the system, whatever you want to do. So if your system doesn't have a particularly secure boot setup, someone can just reboot you to a rescue disk, backdoor your machine, and boot it back up again. So it doesn't matter how secure your system is, someone can just basically backdoor your machine at the boot level. And these tend to have very, not great security. Here's an example of some of the new kind of next-gen KVMs you see out there, like Jet KVM, Tiny Pilot, et cetera. And they're definitely better than like the old-school Raritons, but they still have their quirks. The other one I like to play with a lot, especially in OT environments, is serial port servers. These things are just generally dumb as a brick. You've got a real-time OS or a Linux device, and it's mapping a TCP port to a serial port, and that's it. So if you connect to the TCP port, you're dropped onto the serial port. And if someone connects to that serial port and they log into the device actually has a login shell, great. They never log out, though. There's no such thing as log out in serial. So you can have inactivity timers, but typically if the admin logs into a device of a serial and they disconnect, you follow up right behind them and drop right into authenticated shell. And this is everywhere. You keep all over the map. You always find these authenticated serial port sessions, and the ones that you still find these days, the ones that are like multiplex. So, for example, these real port devices from Digi, they're on like port 771, and the same port talks like 16 different serial ports all at once. So you can't just like scan it and get a shell. You have to like use the Metasway module for it, or build your own like multiplexer. But when you find one of these things, you have 16 shells. It's great. You can basically talk to the entire rack of devices, and half of them are still logged in, because people always forget that there's no such thing as log out on a serial port. Console servers, serial ports, kind of the same thing, but effectively some of these things you can actually interrupt the boot sequence. You can go into the ROM, you can replace the boot ROM, things like that. So effectively the same as like a KVM, but for an embedded device, you can do some terrible things. And then BMCs is kind of my favorite thing lately. This is what I spent the last few months banging on. I love these things because if you can break into the server, you can take it to the BMC. If you can take it to the BMC, you can take over the server. So BMC, if you're not familiar with, is every server that's worth buying these days has a separate crappier computer bolted onto it, and it's on the board. It's typically an A-speed chip that's an ARM-based processor. It's like intertwined with all the motherboard bits. It shares a bunch of buses, and it's got its own network card. It's got its own everything. So if the computer itself is completely turned off, your lights out module is still turned on. So these things are called DRAX or iDRAC or ILO or Oracle LOM, Lenovo XEC. There are a bunch of names, Supermicro IPMI, but they all basically do the same thing. It's a little ARM machine running on there, a 32-bit ARM box that has its own NIC that runs totally separate from the OS, that if you are able to get access to the host machine, you can almost always reflash, take over the BMC. And if you can take over the BMC, you can almost always take over the host OS. So they have this kind of symbiotic relationship where you're kind of stuck with the lower of the two securities no matter what happens. So these devices have some pretty scary bus access. They have like, KCS, LPC. LPC is actually how it gets bridged to the TPM as well, SPI, IPMI, all kinds of fun stuff. There's a PCI bridge, which is actually kind of funky to play with. As of like 3 a.m. last night, I finally got a remote RAM right of the host machine from the BMC on Supermicros. So that was really exciting. That'll be more for DEF CON and stuff, but the neat thing about that is you can, the thing that's been holding people back from doing straight RAM writes has been, if you're on the BMC, you don't have the bus master on the PCI bus. However, you can just tell the BMC to set a certain register, and then it becomes a bus master, and then you can do it all from there. So yeah, the IMMUs stop you, but that's kind of one of the fun upcoming zero day in this stuff. So the AST 500s, this is an older model. They got tons of different buses to connect all your stuff. Kind of trust both directions. If you're able to get root on a machine, you can then reflash the IPMI card without a password using the KCS interface if it's enabled. And if you get into the BMC one way or another, you can typically do horrible things to the host. Even if you're just like taking over the KVM, you can reboot it. But there's many worse things you can do in terms of read-write memory, mess with EPROMs, dump passwords, things like that. Or as of last night, being able to actually write directly into kernel memory below the 4 gig page mark. So KCS is the way that you talk to a device not over the network, over this kind of internal bus on the host. And if you are a bare metal hosting provider, the very first thing you want to do is turn off KCS. Otherwise, every one of your customers can permanently backdoor your bare metal forever, and you can never get them back out again. There's no way to reset the system after it's been reflashed, because once the machine has been reflashed, it can fake itself from being reflashed again. There's even a well-known campaign called ILO Bleed where someone did just that. They took a version of the HP ILO firmware, backdoored it, flashed it onto a bunch of victim machines. One of the victims applied an upgrade to it. They saw the version change, but the background image didn't change. and like, hey, this is ILO5, it's supposed to have a different picture, not this one here. And because the attackers forgot to change the picture of the backdoor former, that's how they got busted. So that was a neat kind of nation state attack. There's all kinds of fun buses, things you can do in that. Won't get too into it here. But effectively, if you're in the BMC, you can get to the host. If you get to the host, you can get the BMC. And hopefully we'll make that point really clear a little bit later this week at DEF CON. There's also the Redfish interface, which is just HTTP REST, but has some like quirks to it. Some output for some scanning. You can still basically dump password hashes remotely through RACP. Yeah, it's all kinds of like these BMCs speak all sorts of protocols that are really insecure in the first place. And once you get into them, it's very easy to get into other ones. And typically, if you get into one, you get into the other. And what a lot of folks do is they connect all their VMCs into the same managed network. So if you compromise one VMC, you can get to all the VMCs, which gets you into all the servers, gets you into the entire company. Because people don't put each VMC on its own VLAN. So one of the neat tricks I worked on is like, okay, if I find a BMC on the internet, can I find which host it's associated with? Like, without knowing anything about the host itself, can I take hints about the data from the BMC itself and find the machine it's actually attached to? And I got some pretty good results. You can actually dump a bunch of stuff pre-authentication, like HPI has this XML data backend, and you can basically get STB ARP cache, things like that. So effectively dumped all the BMCs on the internet, then scanned the /24 every BMC was on, and tried to find out where the host machine was for the BMC. And it worked out pretty well. It actually got pretty close. So I got about 971 matches out of 6,000 where it was kind of in scope. And about 72% of them, the host machine was on a totally different IP subnet than the BMC itself. And I could still find it by matching it all together. So yeah, it's kind of a neat trick. How do you find the host? How do you find that? The important part of this for Bloodhound and attack paths is once you know the relationship between the BMC and the host, now you know how to get there. You know which BMC to compromise to get to which host, and that gets really important. And once you know which host it is, that kind of lets you traverse the graph in ways that are difficult to find otherwise. So an internet scan with BMCs, there's still about 51,000 that speak IPMI on the internet. It's pretty awful, and we'll go into more stats here a little bit later on. This is a preview of some of the work we're doing later this week, but effectively, did an internal sample, external sample, kind of give you a sense of how they go side by side. But effectively, before all the work we did, about 2% of the BMC's internet you could break into trivially. After all the bugs we did, you can now break into about 21% of them. And then internally, that number is about 30%. So the exposure rate goes from about double or more internally, and 15x on the external side because of all the new vulnerabilities that we identified in this work. So an example of all the vulnerabilities, H3C, Dell, Supermicro, Lantronix, et cetera. So lots of vulnerabilities. This started off with 600 different issues getting triaged down into that. So anyways, with that, I'll skip ahead a little bit. I want to talk a little Run Zero Hound is the thing we use to do all this work. You can get it at this URL here, Run Zero Hound, Run Zero Inc, Run Zero Hound. It'll eat all your data, create nice Bloodhound graphs, and hopefully let you do this type of stuff. So thank you very much. Yeah, hopefully. Thanks so much. Sorry for going almost over there.
Don't worry. There's a lot to talk about.
Oh yeah, it's fun. We have a 300 slide deck that's for Black Hat. I'm trying to chop down.
Take a breath, man. You did great.
Slow down later.
Okay, everybody. So the next speaker will be showing up now. His name is Diego. He's coming from Brazil, and he's going to talk to us about Windows kernel vulnerabilities and how to find them. So have a seat, enjoy. Just give us a minute to transition. Like 10,000. I'm just gonna remind you all of the photo policy again. Please don't take photos without someone's express permission. That includes the backs of people's heads. You can get a photo of the slide, or this is being recorded so you can go watch it later.
Hello everyone. Today we are going to talk to finding vulnerability in Windows kernel drivers, and we are going to perform bring your own vulnerability driver attacks. First of all, who am I? My name is Diego Telaroli. I am from Brazil. I'm a cybersecurity analyst at Rakai Security. It's a company from Brazil. I have 5 CVS. This is my blog. This is my website, in case if you want to know more about me. And I also have the OSCP certified. So why are we going to talk in this talk? We are going to talk about introduction to bring your vulnerable driver attacks, how we can find this vulnerability in these Windows drivers, and how we can kill EDRs and antivirus with this technique, this bring your own vulnerable driver attacks, and some real life examples that real ransomware groups are using in the wild. So first of all, a brief explanation about how this is being used in the wild. We have, for example, Lazarus Group, Ghost Engine, Black Byte, a lot of ransomware groups using this exactly technique to kill the EDRs and then deploy their ransomware. So it's a technique that's been exploiting in the wild. A lot of people are using this. It's likely to kill the EDRs and the antivirus, and then drop their malware, drop their stuff, drop their ransomware, and their malware stuff. So we can see that a very hot topic. So first of all, we need to know what even is a driver. Okay, driver basically is a software that's going to operate as a bridge between this operation system and the device. So we can say that the driver is a software that operates on kernel level to translate instructions from the operation system to the device. So if you want to use a printer, for example, it needs to have code, and the driver is going to translate the instructions from the operation system to the device, so we can, from the operation system, use the device and have this communication. So basically here we have an application in user mode, the operation system, and the device, the driver devices that are running directly into the kernel. So driver is the software that's going to translate the instructions between software and hardware. And what's the attack? How the attack works? How the bring your own vulnerable driver attack works? Basically, the attacker is going to deploy a vulnerable driver into the compromised machine. So the attacker compromised some machine, compromised some server, and he wants to exploit the driver to gain access to the kernel. So the kernel is running in the most privileged context, and the drivers are run onto the kernel. That way, the attacker, he's going to compromise the machine, and he wants to run code directly to the kernel. He's going to deploy the vulnerable driver inside the compromised machine, and that way he's going to write a user mode exploit that's going to communicate with the driver, and that way is going to exploit the vulnerability directly to the kernel. So basically, in simple words, the attack here, the attacker gets access to the machine, and he wants to execute some kind of attack directly to the kernel level. So he deploys the driver and then execute the exploit from user mode to gain access to the kernel and run whatever he wants. So as the kernel is the most privileged context on the operation system, he can do whatever he wants. So here is the flow chart. The attacker here identify a vulnerability in the Windows drivers, deploy these drivers onto the compromised machine, and that way he's going to make the kernel manipulation, for example, for disable security controls like kill EGRs, kill antivirus. He can manipulate the kernel and do whatever he wants once he's on the kernel level. In our case, we are going to, it's like this one, we are going to deploy our driver, our signed driver. Our driver is signed by Microsoft. We are going to deploy our signed driver onto the target machine, and then from user mode, run our exploit that will disable the security controls, and then we can, for example, run some kind of ransomware. So this is the bringer of vulnerable driver, and then we are going to make how we can find, first of all, how we can find a vulnerability in the drivers. Okay, So first of all, we have chosen our target. It's called TrueSite.sys. It's a driver from Rogue Anti-Malware driver, and we can be found to download in lawdrivers.io. And here's lawdrivers.io that contains a lot of vulnerable drivers. So from an attacker's perspective, if you want to exploit, we want to make the bringer of vulnerable driver attacks, we need to find some vulnerable drivers. And law drivers have a lot of vulnerable drivers, sometimes even with the exploit, and we can use lawdrivers.io to get, to know the vulnerable drivers and then use in our bringer of vulnerable drivers. So this picture is from this week. We have here a lot of drivers from this month, and it's interesting because these drivers are actually signed by Microsoft. So if you download this driver and just deploy into the Windows, we can do that because it's a signed driver by Microsoft. It's a trusted driver, and there will be no problem. We can do that. And how it's a vulnerable driver, we can just exploit that, as I'm going to show you guys. So the vulnerability we want to find is a vulnerability that's going to kill antivirus and the NDR stuff. The vulnerability relies on the driver's IOCTL handler, so we can send the IOCTLs to the driver that there's no a check if the IOCTL is being called from someone that can call the IOCTL. And then the IOCTL will call the ZW termination process function that's going to arbitrarily kill a process inside the operation system. So let's get it started. I choose IDA Pro to reverse engineer the driver, and we are going to find this vulnerability right here. So it's going to, we need to find an IOCTL code that's going to call a function that will allow us to terminate arbitrary process. So we can load the driver on IDA Pro, and here we have the driver entry. Here is like the main function from the drivers, and here we have the assembly code. And we are looking for a function that can, from kernel mode, terminate arbitrary process. And in the Windows API, we have this function right here. Is the ZW termination process. It's a low-level function in Windows that's primarily used in kernel mode. So this function is only in kernel mode, only driver code. And this function allows to the kernel to kill a process in user land. So when this function is being called, it will kill a process directly from user mode. Then if we found some way to manipulate this function inside a kernel driver, we can arbitrarily kill another process and disable the antivirus the defenses mechanism. So here the syntax, we pass the handle of the process when to kill, and the stats code for the exit. So let's find this function. We have our target, we have our driver, we want to find this vulnerability, and we can, for example, to search for if this function is being called in the code in the driver. So we can use the text search from IDA Pro. So I want to search if this function is being called in this driver. So we can search for that, and we have here a call to this function. So let's follow this call to see where it's been called, if we can, from user mode, manipulate in any way this function and then call that from user mode to kernel mode. So we find right here, this function is being called. It's using the ZW opening process to open a process, and then the ZW termination process is being passed. So here we have the decompile, and we can see this function have a parameter. This parameter is being used to get a handle to the process, and then is using the ZW termination process function to kill their process. So look at it, we can see this is a function in the driver that accepts one parameter, and from this parameter, it's using the kernel function of the ZW termination process to kill some process. Our question here is, can we, from user mode, call this function directly in the kernel? Can we, in some way, find a way to call this function from user mode where this function is being called? So let's see if we can find references for this function right here, if this function is being called anything in something else inside the driver. So we can jump to X references to this function, and we can see a call to this function. So let's follow this call to see where it's going to take us. And here we have another function. This one right here have 3 parameters, and just do a little check if the parameters are valid, and then just calling the function, passing the first parameter to that function. So probably this function here is just making a check if the parameters, the 3 arguments are valid, and if it does, it just call this action filter, passing the first parameter that's going to be probably the PID of the process we want to queue. So we also need to get to this function. Just this is not enough for us. We need to find a way to get to this function and then later get to this another function. So let's see if we got some reference to these functions also. And here we got this piece of code right here. It's making a verification if this variable is equal to 0x22E044, and if it does, it just calls this function, passing three arguments, and one of the arguments is the PID we have seen before. So this one right here is very interesting for us because this is an ioctl handler function, and just taking a look, it's unprotected. I'm gonna show you. First, before we get in this code, get to understand this code, what even is an ioctl, okay? So input-output control codes are used for communication between user mode applications and drivers. These ioctls are used to send comments to device drivers, such as asking for the device information or performing an action. So if we, as a user mode code, a user mode program, want to communicate with the kernel, we can use an ioctl code to send to the kernel this code right here and send data to the driver. So from user mode, if you want to communicate with the driver, we can send ioctls, that's basically our input-output control codes, to send whatever information we want to the driver to do. In this example, we can send ioctls to performing an action on the device and get data from the driver. So this is how the ioctl works. It's a single D word of 32 bits, where different bits range represent specific fields. So we have here the device type of the ioctl, the required access, the custom, the function code, the transfer type. So this is basically a code the program from user mode will send to the kernel, to the driver, to perform some action, to communicate from user mode to the driver. And before how we can send the ioctls, right? We can use the input-output request packets, ERPs, that are essentially just an instruction for the driver. These packets allow the driver to act on the specific measure function by providing the relevant information. What does that mean? IRPs are basically a package a user mode program will send to the driver, and this IRP will contain the ioctl code and the data we want to send to the driver. So RP will contain the ioctl and the information we want to send to that specific driver. In that way, we can send the ERP packets using these two functions, the create file way to get a handle to the team link of the driver. So create file will allow us to get a handle, and then the function device IO control when we specify the handle, the ioctl code. So this one right here is the ioctl code, and the data we want to send to the driver. So when we call this function, it will get a handle to the driver, send the ioctl code 800, and the data, in this case, the data we want to pass to the drive. So this is basically what's happened. We have user mode here, our application user mode, that's going to get the sync link to the driver and then call the device IO control function, passing the ioctl code and the data. And on the kernel mode side, we have our driver, our vulnerable driver, we want to send their package. And if the package will get the ioctl, and if is there ioctl code registered for that function, it will execute that function. So here we have in our driver our handle function of the ioctls. If ioctl send was equal to 0x800, it will execute some function, and some function will do something. That's basically a way to communicate from user mode to kernel mode, passing the ioctl code. Okay, so connecting the dots before we get to the reversing of the driver. Our user mode application gets a handle to the symlink. The user mode application uses the device IO control function to send the required ioctl and push buffers. The driver will see the package coming from the device IO control, so it passes its defined internal functions. In this case, my control function. So the driver will get the ioctl code. If is there ioctl code defined for the RP it just received, it will execute a function that's passed. And then some function executes, and the RP is complete, and the status is passed back to the user along with anything the driver has for the user. Well, we can simplify that and just imagine like it's a network packet. So we send a network packet to the driver, and the driver will do something with that information, and after that execute something internally and going back to the driver. So a cool way to think about ERP is imagining is like network packets from server to client, but it's in the operation system from user mode to the kernel level. So now we have understood how it works, how the ioctl works, how the RP works. We are going to back to our reversing, and of course understood what's happening. So going back here, we have that function that if v10 is equal to 0x22 is 044, it's going to execute this function right here, passing this parameter right here, then execute this another function, this another function, and then the function ZW termination process, that is the function that will kill arbitrary proxies. So right here we have already a vulnerability. If we send from user mode an ioctl code that is equal to 0x22 is 044, it will call on this function, that will call on this another function, that in the end is going to call the ZW termination process without proper validation. And that will allow us to kill the arbitrary process just to send an ioctl code, an ERP containing an ioctl code to that driver. So let's write our exploit. We are going to use two functions for this from the Windows API. That's the create file away and the device IO control. So that's the syntax of create file away, and that's the device IO control when we specify the symlink of the driver and the ioctl code and the information we want to send to the driver. This is a function we want to get the PID of the process. So when we kill the antivirus or the EDR, we want to get back. So we will constantly going to get back. So we don't want that. We want to the antivirus, the defense mechanism, to get that, and we get the PID of the process name to constantly keep killing this process. And here, for example, I use the MSMPng, that's the process of EZET's antivirus. And we then call the crash file away to get the symlink, and the device IO control to get to send the REP package containing the ioctl code. And then we put all it together inside the infinite loop for constantly keep killing the process. And if EZET tries to come back, just killing that doesn't make, I don't want EZET to come back, so keep sending the ERP packets that will constantly keep killing the process, and the antivirus will not come back. So now we have our exploit code, and we have our vulnerable driver. So let's deploy the vulnerable driver and see what's going to happen. To deploy, we can use the sc.exe to create a service from the kernel that's going to load our driver. It's interesting to talk that this is a signed driver, so it was recognized by Microsoft, so we are not going to get in trouble for that. We can deploy the driver without problems. The operation system will allow us to do that. So that was the exploit, the complete exploit. We have the infinite loop right here. We constantly keep getting the process name, the PID of the process we want to kill, and keep sending the ARP packets with the octocodes to keep killing that process, and then deploy our malware, for example, for our answer, for example. So let's run the exploit. We have right here the Zet antivirus and the service running. And we have right here trying to download the robios.exe. And we are being blocked by a Zet. But when we see the driver is loaded, we run the exploit, and it's going to be killing the Zet antivirus. We cannot interact with the antivirus anymore. It's dead, the service is dead. And then when we run the Robios, it will execute anymore without the block from the antivirus. So from the Zet, we have killed the service and then execute a malware we want to. So this is the flow chart. We register the driver as a service, run the exploit, and the exploit will keep killing the process. If it come back, it's an infinite loop to keep killing the process, and doesn't allow the antivirus mechanism to come back and kill the driver. In that way, we can run the exploits to keep killing the antivirus, then deploy unstealer, deploy enhancer, and whatever malware stuff we want to deploy once the defense mechanism is dead. Another example, this is from this week. We have the mon process x.sys is a driver from is a signed driver. So at this time, this driver is signed, and this driver has this exactly vulnerability. So I think it's very cool to show you guys. This is from loud drivers, and we can see the date right here. It's from this month, and I just changed the exploit to get symlink to this driver, and then again keep sending the packets to kill the antivirus mechanism. But in this case, this is a signed driver, and I'm gonna kill some EDRs with this driver exploiting this vulnerability. So here's the exploit, and I'm gonna show you the exploit for this driver for different EDRs. So the first one, we have the Microsoft endpoint. We have the Microsoft endpoint running right here. And if you try to run a malware, for example, we will give us a sex denied. We cannot run the driver. But we cannot run our malware. We have our driver loaded on the target machine, and we have our exploit that's going to exploit the bringer of one vulnerable driver attack. So we can run the exploit. It will kill the defender endpoint, and then we can successfully run the command to execute our malware stuff, and we have been able to disable the defender endpoint security. The next case is against the Sentinel-1. So again, this is a signed driver. This driver is not malicious. This vulnerability has been found this month, and Microsoft did not put this driver on the block list. And we can deploy normally this driver and then run the exploit without problem. So in this case, we are going to run the exploit against the Sentinel-1 EDR, and we can see it's going to successfully kill the service, and then we have been able to disable the EDR mechanisms without problem. The next one is against Trend Micro. So again, we deploy our vulnerable driver and get our exploit. Run our exploit, passing the process name, and then it's going to be killed and keep killing the process. If Trend tries to come back, our exploit will constantly keep killing the process, and there are RP packets to the driver that's going to be killing directly from the kernel level. So from user mode, our exploit will call a function from the vulnerable driver directly in the kernel that was the most privileged context, and then we can disable any process, any defense mechanism, because we are in the kernel, we have the most privilege on the operation system. And the last one is the Falcon. The same thing happened here. We have our service running right here, and then we deploy our driver, run our exploit. And then CrowdStrike processes are going to be killed, and then an attacker can, for example, deploy their hunts or deploy their malware stuff, deploy whatever he wants to, because the defense mechanisms are beaten. So this is the repository of this exploit. This exploit is working right now. This exploit is working right now. This driver is signed by Microsoft. So if you just deploy this driver in some Windows machine, the driver will not be signed as malicious, and you can run the exploit, and then you'll be able to terminate arbitrary process. Thank you. So as a conclusion, we successfully identify a vulnerability in the Windows driver by performing a static code analysis. So we used AdaPro, and we were able to write our exploit in C that successfully will kill arbitrary process directly from kernel mode. So there are some real-life examples I'm going to show you. Again, this is the notice the news, né? And a real-life example is Cuba ransomware that using this code right here to do exactly the same technique I show you guys. It just get a handle to a vulnerable driver. After that, it will use the device or control function from the Windows API to keep sending dioctal code to killing the process elite. So this is a code of real ransomware group that are using in the world. And if we see, is exactly vulnerability we have seen. It's an ioctl handler that's unsafe. Anyone can call this ioctl right here, and after that we will call the ZW termination process function that passing the PID of the process we want to kill. So same technique and exploits using in real life by real ransomware groups. Well, that's it, guys. Thank you so much. Thank you so much.
Yeah.
Nice to meet you.
Likewise.
Hey, Garito. Oh, thank you so much.
How would you like me to introduce you?
I don't know.
Okay, I'll wing it. Well, he is going to talk to us about the SIM tool that he developed to analyze logs for security intelligence. So he's getting set up. Take a minute, get settled, and I'll just remind you of the photo policy. Please don't take photos, especially with other people in them. You can get photos of the slides, or this is being recorded and streamed, so you can always just look there.
Hola. Hey guys, if you can continue the talk on the outside. So, thank you. Okay, I think we're good to go. Hello everybody, welcome to Flashy. That's this talk. We're gonna try to do two things today. First, solve SIM. So that's a little bit challenging. And the second one, also challenging, is try not to say AI on a 2026 talk. So please make your bets if we can make them. So what is flashy? So when your SIM is too expensive to tell you the truth, who has struggled with their SIM? Okay, so we are on the same page. First, a little bit about me. Who am I? I am Manuel Montes de Oca, also known as Dragon in the cyberspace. I am the co-founder and engineering director at Supra. We are a local company in Peru. We implement cybersecurity projects, as many of you here, I guess. I got more than 10 years of experience fighting on the cyber trenches, mostly like you. And that's how I struggle. I mean, I found this rock in the path, which are called SIMs. And here are my socials, so we can keep in touch after the talk. Okay, you might know us from before. Actually, this project started long ago. We were at the beginning very Fortinet focused, so we started as FortiUnicorn. Then we mutate to FortiDragon, and well, we didn't wanna get sued by Fortinet, so it makes sense to change the name one more time, and also because we incorporate also Palo Alto firewalls, so that's how we end up being FLASI. FLASI stands for Firewall Logs Analytics for Security Insights. But we kept the dragons because dragons are cool. We are also cool. So enough about me. What you guys need to be here. So you need a firewall that produces logs. Okay, raise your hand if you relate to this. You need a firewall that produces logs, and you need to make a report out of it. So if it's a firewall that is like shut down like 3 days ago and nobody really cares about it, maybe this is too over-engineered for that. And most importantly, you need a firewall that produces logs, you need to make a report out of it, and a human is actually going to take some action out of it. I mean, someone is actually gonna read the report, which sounds like a little bit disruptive, but it happens sometimes, and you need to take some action, whether it's like doing some fine-tuning or doing some threat hunting or whatever you need to do with your firewall. But most importantly is what you don't need, and you don't need money. And we're gonna talk about this later, and this is going to be very important. Like, actually, this is not a limitation. This is an opportunity to think outside the box, to dig harder, to find new alternatives. I mean, if you have unlimited budget, of course, you can afford any SIM. But we are all in cybersecurity, and if we have learned something, is that there is no budget that can like get us all the tools we need. We always live on a budget cap. So this is important. Okay, what is the real challenge about SIMs? What do they bring to the table? Why do we need them in the first place? Well, they bring the promise of correlation. So what is correlation? Well, let's look at an example. We have one IP that is making a connection to another IP, and that's a ping. It's doing a ping. One IP is pinging another IP. Okay, and the connection has been accepted by our firewall. That very same IP to that very same destination IP is now trying to do SMB, and that has also been accepted by our firewall. So these two events in isolation, they don't look such malicious, like they might be normal in our network, but let's look at the forest. So we have that very same source IP that is connecting to more than 2,000 different internal IPs, And it's targeting several protocols: ISMP, SSH, Telnet, SMB, RDP, and it's performing one attempt every 30 seconds. So this is clearly someone trying to scan our network, performing an scanning. This is clearly malicious. But what's my point here? My point is that for jumping into this conclusion that there's a malicious activity, we need all the logs, all the events, all the logs. We cannot jump into that conclusion just by looking at one of these logs in isolation. Neither one of these in isolation. We need the whole. Why is this a problem? Because it's pricey. SIEMs charge us for the amount of data we put in, either EPS, events per second, either data retention, like if this has been in the spread of an hour, maybe that's fine, but if it has been on the spread of 1 month, maybe that's a lot of data. So imagine a firewall that charges you for every connection. You would not use it. The business model of SIEMs are trying to push you away from using the SIEMs. So that's the real problem. And what do they tell us in order to size them? Hey, you got to tell me how much logs are you going to put in. But it's impossible for any of us to estimate that. We hardly have a raw estimate. And even if we do, that could increase in time. Like we can start with, I don't know, let's say 10,000 EPS, events per second, but next month it could be 15,000. And we don't know it. Like the conditions in our environment can change. And most importantly, they should change. It should increase because we should be fine-tuning our network to get more visibility, not less. We need more logs. So we are forced into these two options. We either drop logs or we go bankrupt. So who here has actively dropped logs on their SIEM? Yeah, that's a real problem. Nobody wants that. It's something we are forced to do. So what do we do at Flashy? Well, we try to solve this challenge, and we learned it the hard way. Actually, our history starts with this news almost 10 years ago. Fortinet dives into SIEM market with the acquisition of BsidesLV. So at that time, my question, my first reaction was, like, what the heck is even a SIEM? Like, I had no idea. So I asked a friend, like what we all do when we didn't have ChatGPT, you know? So he told me, it's like FortiAnalyzer. You guys know FortiAnalyzer? Raise your hand. Yeah? Okay. So it's like FortiAnalyzer, but for any device of any vendor. And at that moment, my mind just exploded. You know, I couldn't believe that such a powerful tool could be even possible. Was it possible to learn that power, to master that power? Not from open source, I got. Well, we all know how the story continues, and we all know it's not good. We had to go all in FortiSIEM just to find out that that was not the path to the enlightenment. Because very, very, very soon we reached this point. As I was saying, SIEMs force us to expand them, and there's no budget that can stand that. But the problem is not only the budget. I mean, we can go rob a bank and problem solve. But the real problem is that SIEMs don't even care about firewall logs. And let's look at this alert. This is a real alert that we get from a SIEM. Let's look at the source IP. The source IP is 10.147.162.9. That's what the alert of the SIM is telling us that it's the source of the attack. Okay, this is an attack. As we can see here, this is an attack alert. But if we look at the raw log, we see a different source IP. It's completely different. So what is that source IP on the SIM? I mean, how has the SIM understood what that value means? Well, we see that it has parsed it as a post-NAT source IP. So if it had been a translation, an IP translation in the connection. But this is a IPS log from a Fortinet firewall. And this type of logs don't carry any NAT information at all. So this is clearly an error, a bug, if you will, in the parser. So why is this dangerous? Or why is this so bad? Imagine we have plugged this alert into a playbook that is blocking all the attacker's source IP. So that source IP would have ended up on a block list. And what is that source IP anyway? Because where do we see it? I mean, we don't see it on the raw log. Well, that source IP is the source IP of the firewall itself. Yeah, so that's pretty bad. Imagine if we block the IP of the firewall, then we are blocking the whole branch or even the whole headquarters, or, I mean, it will be catastrophic. I mean, what would happen to any of us if we block the firewall's IP? Like, we will be fired the next day, just because our SIM had an error. So it's catastrophic. So this is the moment where we hit a bottom. We said, okay, we cannot continue this path. We need to look the light somewhere else. But first, we open a ticket, Parser is wrong, we open a ticket, what everybody would do. So the FortiGate parser is wrong. And support told us, hey, there is no support for it. So the actual Fortinet support told us this, but because they don't support parsers, because they are supposed to be like handmade, but hey, it's your parser. I mean, it's the parser for your product. Well, there is no support for it. So this is the moment where we needed to look somewhere else. And we said, hey, but okay, let's fix it ourselves. So, I mean, what the heck? Up to this is actually the parser, the code. No? The code that receives the string and saves it on the SIM, the storage. So up to this day, I don't know what any of this means. I have no idea what this code does. And if you guys want to troubleshoot this, I want to let you very good luck, because it's only about 8,000 lines of code. So good luck with that. This is the moment where I was saying we looked somewhere else and we found this. We found the KB function of Logtash. Logtash is an open source ETL. It's part of the Elastic Stack. I mean, an ETL is just a fancy word for a program that collects information or data somewhere and put it somewhere else, like pre-process it, clean it a little bit, and save it somewhere else. So why is this important? Why is this function important? As the name says, it gets a string that has a particular format, key value format, like we're seeing there, and splits it. It only does that. Very simple. It splits it on its keys and its values. And why was this important for us? Because that's how exactly how a Fortinet log looks. So it's a massive string with a lot of key value pairs. We don't know which key value pairs are those beforehand, before we receive the log. So we just need to somehow dynamically split them. And that's exactly what that function does. So this function let us go from this to this. 3 lines of code. Magic, black magic for us at the moment. We went from the 8,000 lines of code to only 3. So it was love at first sight with us and Logstash. That's how we started our path with Elasticsearch or the Elastic Stack. Who knows where this place is? Any idea? You? Machu Picchu. Well, that's actually not that right. I mean, it is. Huayna Picchu, yeah. Like the ruins we see on the bottom, that's actually Machu Picchu. The picture it has been taken from Machu Picchu, but the mountain at the back is Huayna Picchu. And it's really cool. You can go there on a nice walk if you are brave enough, because that walk is called the Stairs of Death. And if you've been there, you might have some nice pictures like this one, where you have the cliff on one side. So good luck with that as well. Why do I bring this? Because managing the Elastic Stack feels a lot like doing this path. It's very complex. I mean, there are lots of concepts: index, shards, islands, mappings, templates. Like, I'm not even half of what you need to know to successfully manage an Elastic Stack. Elastic knows it. So that's why they launched the Elastic Cloud Serverless service. So this is great. This works fluently. It's very smooth. You get rid of all the complications. This is awesome, but it's expensive. This is how much it costs us, like a cluster managed by Elastic, but I mean they are service for a particular scenario, a particular amount of data, of retention, of firewalls, etc. And this is the same on serverless for that very same amount of data, of firewalls, and retention. So it's like a 20x increase. So we don't have money, so this was not viable. So we kept looking for other alternatives. That's how we found QuickWit, which I would say is like the open source serverless Elastic. This also works great. I mean, it was a startup. The performance was awesome, but it got acquired by Datadog, so it got discontinued. I mean, history repeats. Like the history of all acquisitions, you know. And that's how we ended up on Victoria Logs. This is what we currently use as a backend. This works great. The best thing of it, it's not only the performance, which is very good, but the best thing is that it's schema-less. So that means that we don't have to specify how the data is gonna be beforehand. Like, for example, if we have a field that is a source IP or an IP on any matters, we don't have to specify that it's an IP. We just send the data, the field value, we send it to the storage, and it will know it's an IP. So this is very good. This is a unique feature of them. So this is our current stack. We support more than firewalls now. Of course, firewalls are our main reason to exist. On the ingestion side, we moved from Logstash. I mean, it was good, but it's also kind of old, and we now use Vector, which is Rust-based, and it's really smooth. On the storage side, as I said, we now use Victoria Logs. We kept supporting Elasticsearch. We tried Loki. Don't try Loki. That's not good. We want to try greptinedb. Sounds really good. And as I said, QuickWit was deprecated. And for visualization, we use Grafana if we want to see the logs in Victoria Logs, and Kibana for Elasticsearch. So let's go a little bit deeper onto one of these phases, each of these phases. First, the data sources. We can give a whole another talk about the data sources, I mean the data sets of the firewall vendors. Actually, we needed to do 2 more projects, 2 more repos. Palos for PanOS log scraper, and Flores for FortiOS log reference scraper. So what do I mean? I mean, we got the data set, I mean the actual official documentation, and we compare it to what we were getting from the wire, we see a lot of things that needed to be corrected. But this is not a critique for the firewall vendors, because for anyone who has done data analytics, they know that step 0 of every project is cleaning your data set. That's always going to be the case. This is a critique for SIEM vendors, because they have not done any of this. Any of the let's say bugs we found, nobody has documented them. So I don't know how they parse the logs from the firewalls. So on ingestion, on the actual parser, of course we do a lot of pre-processing, type validation, etc., all the normal things you do at parsing. But surely the most important thing we do is field naming normalization. So what is field naming normalization? Well, exactly as the name says, we standardize the naming of the fields we get from the vendors, from every data source. So for example, on FortiGate, the source IP is called like this. On FortiWeb, it's a little bit different. On Palo Alto, it's also a little bit different. So what's the issue here? If you want to do a query that you want to look for a specific source IP among all these vendors, so you will have to do src IP equals 1111 or src dash IP equals 1111 or and so on and so on. So that doesn't make any sense. So we need to first standardize the naming. So we translate all of these custom names into one normalized name, source.ip. So we have decoupled the logic on the SIEM from the naming on the data sources. So all our queries, all our dashboards, all our rule will use the standardized name. So we can just unplug, plug new data sources, and everything is gonna work the same. So if we have a rule for Fortinet, then that rule is gonna be useful also for Palo Alto. We don't have to change anything because we are calling the standardized name. So we use ECS, which is an open source standard that was invented or created by Elasticsearch, but now has been adopted by the OpenTelemetry, so it's even more standard, more open source. And we are also going to expand this into other naming standards like OCSF and Styx Taxi. Okay, now time for the demo. Okay, so this is the dashboard. I mean, this is the actual dashboard we get. So at the top, the first thing we need to know is that we split the investigation or the analysis per direction of the traffic. So, because it's completely different to analyze outbound traffic than internal traffic. And then we split it one more time for the metric we are analyzing. For example, all this dashboard is going to analyze the sessions, the connections. And we have another dashboard to analyze how much bytes have those connections generated. So what is the most important thing that a firewall does? It blocks. That's why we bought it on the first place. So the action is the most important variable we have. So that's what we analyze at the top. We analyze what actions has the firewall taken over those particular connections. And the action is a broad concept because, for example, in Palo Alto, it's split between three fields, subtype, action, and session end reason. So that's why we have this really nice chart that connects all those fields. We also have it on a time series fashion. We have the rules. We have geo analysis as well. But the most important thing is what we call the dimensions or the entities. So what is a network connection? A network connection is source IP, destination IP, protocol, port, and application. And that's exactly how we want to pivot the analysis. So we have all these all these cool visualizations that analyze the whole data set of the firewall. This is Palo Alto. How would a Fortinet dashboard look like? Well, exactly the same. And this is not by coincidence. I mean, this is intended because we want to remove the abstraction from the user. I mean, we don't want the user to investigate the dashboard, no, to investigate where things are or how are they connected per every vendor. No, we want it to be universal. So it looks almost the same. Of course, there are some field names that are specific to each one, but you can navigate around this like very fluently. We also go very deep into threat. I mean, into what the security actions of the firewall does. For example, in Palo Alto, spyware, URL, vulnerability, wildfire, etc., etc. So this is dynamically from the logs we get. I mean, if you have turned on all the security features, you will have a lot more tabs here. And the same in Fortinet. So we have all the UTMs engines here. So it's pretty broad. I mean, there's no other such in-depth dashboard on any SIEM. And how are we doing on time? Oh, we ran out of it. So, I wanted to talk a little bit about what's next, the roadmap. So I'm just gonna say that up to this point, we are not totally a SIEM. What do we need to be a SIEM? Well, we need alerts, but we don't want to do it the way that every SIEM does it. That is, okay, we have a bunch of raw logs. We like fed some static triggers, and we get alert fatigue. We get like a nightmare of alerts. And no, this is not the way to do it. So if you guys wanna know more, I will be outside. I think we have a minute for Q&A. If anybody has a question, no? Okay. Well, thank you very much.
get started early so that you have like all the time you need. Okay. All right, hey everyone. Welcome to B-Sides. Hope everyone's having a really good time. Yes, absolutely. We are going to go ahead and get started. We have Alejandra Vasquez, an engineer, researcher, and red teamer who has got some really fantastic technology to share with us. So everyone, please give a wonderful welcome to our guest speaker.
Okay. Well, can you hear me well, right? Yeah? Perfect. Okay, so thank you so much for being here. I don't know why are you here, but thank you. Oh. Yeah, like this one? Yeah, perfect. Thank you, guys. Okay, so, well, my name is Alejandro, and what I have put together for today is basically everything I couldn't find when I first started digging into how to compromise the boot process of a machine, whether that's Windows or Linux. So today I'm going to give you UEFI malware bootkits that can modify any Windows or Linux boot process. I'm going to share exploitation techniques focused specifically on attacking the boot chain. I'm going to give you documentation on CVEs with the actual vulnerable binaries, with working exploits and with reverse engineering nodes. Then I'm going to show you how to dynamically debug UEFI components, which is something that nobody has documented properly online. And I will give you the lab environment scripts to set all of this up from scratch, okay? So all of these resources, more than 20 projects, many of them publicly available for the first time, are going public right now. We probably, don't worry, because at the end I'm going to show you the same resources for you to take the picture, don't worry. Well, we probably won't get through every question in the Q&A because there is a lot of material, but you can find our LinkedIn profiles there, so feel free to reach out and ask whatever you need. I'm a very approachable guy, yeah? So with that being said, let's get started. First of all, let me ask you something. When you boot your Windows machine or your Linux machine, how many operating systems do you think you are running through the entire boot process? Most people say 1, but the answer is 2. Before Windows starts, before Linux starts, something else is already running, and that something is UEFI. I see UEFI as an operating system because you can interact with memory, with storage, you can access the network, you can use protocols like UDP, TCP, Bluetooth, and more. And I say this from experience developing UEFI bootkits. It's a complete execution environment that runs before the operating system you are used to thinking about. You can execute applications, you can load drivers, you can do whatever you want using UEFI. Now, every modern Windows and every modern Linux, they all begin here. And here is what actually happens when you boot the system. UEFI firmware runs first. It reads the boot configuration, picks a boot manager. The boot manager picks an OS loader, and the OS loader loads the kernel. Windows kernel, Linux kernel, whatever. So before your OS is running, you already have several UEFI components that have executed, made decisions, and handed control to each other. That chain, firmware, boot manager, OS loader, kernel, well, that's the boot chain, and it's what we're going to be targeting. But the chain is protected. You cannot just drop any random UEFI binary, any random UEFI application onto a machine and have it run, because if secure boot is enabled, the firmware checks at least 2 things before loading anything. First, is this UEFI binary, this UEFI application signed by a trusted certificate that there is in the DB? And second, is its hash absent from the DBX, the revocation list of components that are vulnerable or malicious? If both checks pass, the application runs. Either one fails, it doesn't. It's a bit more complex than that, but let's say that that's secure boot as a summary, and on paper it's a solid model. But it has a lot of ways to break down. These UEFI components are software, and like any software, they contain flaws. Custom PE loaders bypass secure boot checks entirely. The firmware never gets to verify what is loaded next. The DBX only protects you if it's updated. There have been cases where vulnerable signed binaries could be used to compromise the boot process because the revocation hadn't been deployed yet. Then supply chain attacks, like PKFail, show that if a signing key is leaked, every device that trusted it is potentially at risk. And UEFI's own design is not perfect. A good example of that are MB-RAM variables. Those variables are identified by name and a GUID, not by their attributes, which means you can pre-create your own MB-RAM variable from the OS, reboot, and influence what the firmware does the next boot. And attackers are paying attention to UEFI. So am I. Last year we shared Avis, a Windows UEFI bootkit, an evolution of Black Lotus. This year, just a few days ago, in the OFI1 security stream, well, in the OFI1 security channel with Stephen Sins, we shared Antarctic, the first publicly released Linux UEFI bootkit with full source code available, which we built following the same approach as Bootkitty. But beyond malware, every year, new vulnerabilities are discovered in boot managers, bootloaders, and many other UEFI components. The attack surface keeps growing. And here is the thing with non-UEFI attacks. You take a vulnerable UEFI component, signed, trusted, bring it onto any machine you want to compromise, exploit that vulnerability during boot before the OS loads, and from there you can load or modify wherever you want. By compromising UEFI, the OS number 1, you compromise the kernel of Windows or Linux, the OS number 2. Admin rights, a vulnerable UEFI component, and a reboot. That's the primitive behind every known UEFI-based attack. Now let me walk you through what actually happens when a machine boots. You press the power button, UEFI firmware starts executing, it reads the boot entries, the configuration that tells it what to load next, and then the chain begins. One UEFI component calls another. That one might load drivers, another might load additional applications, and eventually one of them load the kernel of your operating system. Now, Windows and Linux each have a predefined boot chain, and I'm going to show you that in a moment, but that chain can be modified, and some software actually does modify it. Some recovery and backup tools, they don't just install things inside the OS, they add their own bootloaders and change how the machine boots. So if one of those components has a vulnerability, you can take that UEFI binary, bring it to any modern machine, exploit that vulnerability during boot, compromise UEFI, and by compromising UEFI, you reach the kernel. Most UEFI CVEs don't appear in Microsoft's own boot components or in the official Linux bootloaders. They appear in signed third-party UEFI components. That's your entry point to compromise the boot process of any modern machine. Following that, let me explain what the unmodified boot process looks like, starting with Windows. Power button, UEFI firmware, boot entries. The default boot entry references a component called bootmgfw.efi, the Windows boot manager, located in the ESP, the EFI system partition under that folder, EFI Microsoft boot. Then the boot manager loads wingload.efi, the Windows OS loader, which loads ntoskernel.exe, the Windows kernel. Linux is similar, but just a bit longer. Assume secure boot is enabled. The first component is shim. Shim calls groovx64.efi, the groove bootloader. Groove loads VM Linux, the compressed Linux kernel that decompresses into VM Linux, the actual kernel image. And from there, the system continues through init RAMs. So that was the normal boot process without modification, without interference. But nothing prevents that chain from being changed. One last time, you take assigned third-party vulnerable UEFI component, register it as a new and primary boot entry on the target machine, you exploit that vulnerability to gain execution, and from that point, you modify the boot process. You hook UEFI components, you patch the kernel, and you execute your own code before the OS security model ever initializes. That's the bring your own vulnerable UEFI component approach. Bring your own vulnerable UEFI application, bring your own vulnerable and signed, whatever. Before we get into exploitation, we need a lab, right? And everything you need to set a solid UEFI exploitation lab up and running is in those 3 repositories, okay? Everything. Once you have that environment ready, the first thing you should learn is how to dynamically debug UEFI components, which is exactly what the next slides cover. I recommend using Chemo instead of VMware, but both let you expose a GDB stub on a TCP port that you can connect to remotely using GDB. Well, using GDB, JIRA Debugger, IDA Pro, whatever. I recommend using Chemo, but it's your choice. With the UEFI environment up and running, you only need 3 things to get started. A UEFI shell, basically a command prompt for UEFI, the UEFI component you want to debug, and a UEFI loader application. And one of the key parts that nobody documents properly for beginners is that you need a UEFI loader application, which loads your target binary, tells you exactly in memory where it landed, and then waits, giving you time to connect from JIRA Debugger and place a breakpoint at the entry point address of the UEFI application or the UEFI component you want to debug. Once that breakpoint fires, you have both views simultaneously. On one side, you have the static pseudocode in JIRA, the vulnerable logic you identified earlier during static analysis, and on the other side, you have JIRA Debugger, showing live execution. So you can step through the code, see which branches are taken, and check or confirm whether the execution actually reaches the vulnerable path. So at this point, you can use this workflow for 2 areas where very little public information exists. Dynamically analyzing UEFI bootkits and dynamically analyzing, I don't know how to pronounce it, but benign UEFI components, good UEFI components, to spot vulnerabilities in them, okay? And well, today we have focused on the second one, so because you need something to practice on, I built VUAC, a vulnerable UEFI application for CV exploitation. It's just a UEFI application with design patterns that mirror those CV vulnerability classes you see on the screen. And we're going to see how we can debug this UEFI application or wherever UEFI application you can find out there. Or whatever UEFI bootkit, you can use this workflow for whatever you want. Well, I'm going to use this workflow to check if my exploits are working or not. So I'm going to set up this UEFI environment. And now that I'm here inside the UEFI environment, I'm going to execute the UEFI loader application. I don't know if you can see well, but yeah. I execute the UEFI loader application, and I specify the path of the vulnerable application I want to debug. So I specify the path, and the UEFI loader application tells me the image size, the image base, and the entry point of that UEFI component. So now I can come here to my virtual machine, open JIRA, and open the same UEFI component I'm going to debug. I'm going to open it. And now I'm going to connect this JIRA instance to the UEFI environment. I just have to click on debugger, configure, GDB remote. I just have to specify the host, the port, and the GDB command. I click on launch. I have to execute a few scripts, and you're going to see that in the middle of the screen, it appears the dynamic section. Okay? So now I have both views, the dynamic section in the center of the screen and the static analysis in both sides. So I'm going to copy the entry point of the UFI component I want to debug. I'm going to copy it, and I'm going to look for it in the dynamic section, in the dynamic window, and place a breakpoint at that others. And now I click on run. I'm going to write yes in the UFI environment, click enter, and the breakpoint fires. So now I'm debugging this UFI application, this vulnerable UFI application dynamically. But it's not synchronized. The dynamic window and the static analysis is not synchronized. So I need to add a static mapping. Here, well, you just have to do some calculations with the image size in the image section. And once you have it, you can see that now the static analysis and the dynamic analysis is synchronized. I need this kind of workflow because I have spent, well, some months looking for vulnerable UFI applications, and in order to check if the exploits work or not, I need this kind of, I need to check if the exploits work or not using this dynamic analysis, because if, you know, with the static analysis, I don't know if something is working or not. So I can place a breakpoint at other address, click run, and it's going to reach that point. It's going to reach that point in the UFI application. So at this point, we have the resources. We have the foundation on what an attacker is going to do to compromise the boot process. We have the environment, the debugging workflow, and the practice target, right? Now look at the screen. This is what is actually out there. And there are, well, so many more vulnerabilities, but at least this gives you a picture of the past few years. I want you to look at the left side of this timeline, that 2022 vulnerability, a custom PE loader. Now go all the way to the right, 2026. 4 years later, same vendor, same design mistake, same outcome. And that raises a question worth asking. When a CVE is assigned, for example, when the CVE 2024-7344 was assigned, did that vendor fix the actual design problem? Did they keep shipping vulnerable binaries in newer releases? What happens after a secure boot bypass CVE gets assigned? Because this is not a normal CVE that affects, you know, a binary inside the OS. This affects UFI. And a flaw in UFI can compromise everything that comes after it. Here you have 2 different products, 2 different CVEs, and the same design mistake. A Microsoft signed UFI application that includes a mechanism to load another UFI application, but without going through secure boot verification. If you find something like that, a custom PE loader, you can load anything. And loading anything means loading a rootkit. And once a rootkit is running, well, you're fucking done. There is no protection inside the OS that can save you because the compromise happened before the OS even started. For CVE 2024-7344, you will notice there are 2 QR codes. Well, the QR code below links to research I did a couple of months ago to check whether the vendor was still shipping vulnerable binaries in newer releases. I think it's worth reading because the vulnerable binaries and the exploitation box are there. So enjoy it. I mentioned earlier, more or less, that UFI wasn't perfectly designed from a security standpoint. One of the clearest examples of that, as I said, is how MBRAM variables are used and trusted through the firmware ecosystem. This is extremely widespread. Okay, there are countless CVEs where NVRAM variable values are used as configuration that firmware components trust blindly. But I think these two CVs from 2025 are one of the best known examples of it. Both show how controlling an NVRAM variable before the reboot can let you influence what the firmware does the next boot. And you will find my exploitation notes for both of them in the QR codes. So we're going to reverse engineer a few of those vulnerable binaries that are related to these CVs, starting with the CV 2026-25250. I'm good to look at the properties of this UEFI application, shdloader.efi. And as you can see, it's signed by a Microsoft certificate, while using a Microsoft certificate. And now I'm going to look at another UEFI application called shield.efi, and it's not signed at all. But the first UEFI application includes a custom payloader to load this shield.efi. So we're going to open the first UEFI application, and using a Jitter script, we're going to locate the exact function where those loadings are happening. So I execute the Jitter script. I share everything, okay? The Jitter scripts and the exploits and the vulnerable binaries, so don't worry. I'm going to look at the function, and if I go down just a little bit, I see, and I could perform more reverse engineer operations to see that that function is a custom payloader, and is trying to load EFI boot shield.efi. And that shield.efi is a UEFI driver. So, well, I can change that UEFI driver for another unsigned UEFI driver and do whatever I want in the UEFI and reach the kernel. But there is something missing here. And I'm going to explain to you what is missing using another vulnerable binary. Again, this binary is trying to, well, what I'm going to do now is executing a script that I already executed. And it's going to, that script is going to look for this NVRAM variable. I know that EHC parent buffer, that is the name of an NVRAM variable, but I don't see any UEFI function being read, like get variable or something like that, right? So here, there is something that I don't share, and I don't share Behemoth. Behemoth is a tool that allows me to spot vulnerabilities very, very easily in vulnerable UEFI applications, okay? I'm going to share it at the right moment. One of the first versions of Behemoth allows me to create a GDT file, the most updated GDT file, that I could include in Jitter. And now using another Jitter script, I could retype the entire program. And this allows me to spot those vulnerabilities very, very easily. Those custom payloaders and those NVRAM variables being read and then use those values in unsafe ways. So now you see that get variable, that function is there, and I have retyped the entire program. So now finding vulnerable UEFI, now finding vulnerabilities in these UEFI applications is more easily because I have retyped the entire program. It's more close to the source code. And the last, the last part of the demo is just, well, in one of the last packages of the software sysreturn related to the CV 2024-7344, in a specific folder, they were shipping the vulnerable binaries in that package. Not anymore because I have contacted the vendor, that Taiwanese guy, and now they have deleted the vulnerable binaries. So there are no more associated, well, I don't know, but at least there are no vulnerable binaries related to the CV 2024-7344 in the newer releases of the package, of that software. So, at this point we have almost everything. We have the resources, the environment, the CVs, and the vulnerable binaries. But there is still a few fundamental techniques we need to understand. Or rather, a few questions you should always ask yourself when looking at a UEFI vulnerability. For example, can I modify a pointer or a structure to bypass a security check? Can I abuse the NV-run design issues we talked about? Which variables can I influence? And from there, you will naturally end up asking questions like, how do you hook boot services and runtime services? What boot services and runtime services are? How do you modify memory from UEFI to patch the kernel once it's being loaded? Things like that, the kind of questions that led you to the techniques you end up using to exploit that specific vulnerability. And now I'm going to try my best to explain at least the first three. Well, I guess you know that, but I'm going to explain it anyway. UEFI components are built using the UEFI specification. Most of them using the EDK2 framework. And the EDK2 source code is public. So when you want to understand how secure boot enforcement actually works at the code level, you can just go and read it. And what you find is that when a UEFI image is loaded, there is a specific global pointer called gsecurity2 that gets consulted. If that pointer is valid, the firmware performs signature verification. But if it's null, that check is skipped entirely. So if you have any kind of write primitive, you can null out that pointer and secure boot enforcement disappears at runtime. But the firmware still reports secure boot as enabled. So from the OS's perspective, nothing changed. But now unsigned UEFI images, UEFI bootkits, can execute freely on the machine. As I said, NV-run variables are identified by their name and a GUID, not by their attributes. Whether they are volatile or non-volatile, well, that's not part of their identity. So if you are representing a UEFI binary and you notice it's reading an NV-run variable, well, that variable immediately becomes interesting because maybe that UEFI component expects to create a volatile variable during boot, but if you pre-create a non-volatile variable with the same name and GUID before the reboot, well, your variable is going to be already there when the firmware looks for it, and it reads yours. So depending on what that variable is used for, the impact can vary from controlling an NV-run, well, from controlling a configuration flag to controlling which certificate gets trusted, as in the vulnerability called hydrophobia. So whenever you are representing a UEFI binary and you see an NV-run variable being read, ask yourself if whether NV-run variable shadowing attack could apply. You may not know this, but Linux has a security feature called lockdown mode. And when active, it restricts things like loading unsigned kernel modules. In a secure boot enabled environment, the kernel enables this mode automatically. But how does the kernel actually decide whether to enable it or not? Well, if you go read the kernel source, in a specific function, it reads that variable, mock secure boot state runtime. And with that, if that variable is volatile and holds a value of 1, well, the kernel doesn't enable that mode at all, even if secure boot is fully active at the firmware level. So if the kernel doesn't enable that mode at all, what you can do? Well, you can load unsigned kernel modules, Linux kernel rootkits. And that's why these variables matter so much. A single NV-run variable can completely change a security decision the operating system makes during boot. And you can do something very, very similar in a Windows environment, but just to, you have to modify another NV-run variable, and you will be disabling well, another protection mechanism, VBS, virtualization-based security. And now we're going to look at these techniques. So here I am inside my UEFI environment. And the first thing I'm going to try to do is executing a UEFI, well, a hello world.UEFI, okay? but secure boot is enabled in this UEFI environment, so it's going to fail because it's not signed. That UEFI application is not signed at all. But I'm inside a signed UEFI shell, and there are a lot of Microsoft signed UEFI shells out there for you to use. So now using the mm command to modify memory, or using an application that I have developed for you to understand this technique, just as a proof of concept, I can nullify the G-security2 pointer. And once I nullify it, I can execute hello world.efi. I'm going to do the same just in a few minutes to load a Windows UEFI bootkit. So this is a very, very powerful technique that's out there since, I don't know, since when I saw it in 2020, but you know, it's there since UEFI was there. Now, we're going to see how NVRAM variable shadowing applies, or what NVRAM variable shadowing is. The first thing I'm going to do is execute gate.efi. And gate.efi creates a volatile variable during boot, and the program finishes, right? Now I'm going to execute ingest. And don't worry, I give you scripts to do what ingest is going to do, because you don't need to execute ingest. You can execute scripts that I'm going to provide you from the OS. What ingest is going to do, you can do it from the OS, okay? It has created a non-volatile variable, but with the same name and UID. So now that I execute gate again, it tries to create a volatile variable, but it fails because another non-volatile variable with the same name and UID is there. So it completely changed the outcome and finishes with another how it's called, in another branch of the program. Okay, let's call it that way. Now I'm going to go to my Linux machine. I'm going to execute this script that tells me that secure boot is enabled and Linux lockdown mode is enabled with that variable, with that value, sorry. And I'm just going to power off the machine, enter an EFI shell, and execute a UEFI application that modifies the variable of that NVRAM, the value of that NVRAM variable. So now, when I load the Ubuntu kernel, and I execute another script, I can see that secure boot is enabled. We have disabled Linux lockdown mode, and well, the script is there for you to see it. We have been able to load a loadable kernel module. This could be a Linux kernel rootkit. Okay, it's just a proof of concept, but just for you to see that you can load whatever thing you want in the Linux kernel, and well, you couldn't do it, but yeah, you can if you know what you have to modify in the boot. So let's put everything together. We have the environment, the CVs, the vulnerable binaries, the debugging workflow, the tools, the exploitation techniques. We have everything we need. The only thing we were missing was a complete UEFI bootkit for Windows and Linux. One that, by abusing one of those vulnerabilities and exploitation techniques, could be loaded during the boot process to modify it before the operating system even starts. And that's exactly what we have shared. We have shared Avis and Antarctica. So here you see that CrowdStrike Falcon sensor is installed on the machine. Secure boot is enabled as well. And I'm going to execute one of these scripts to bring a Microsoft signed UEFI shell as a primary boot entry. And well, using that shell, well, first I have to execute the script. Don't worry, because I share the scripts, I share everything. So don't worry, you can test this at home. I have bring that signed UFI shell. Now I can restart, and the UFI shell is going to appear during boot. So now I repeat. Well, you don't need to use the mm command. You don't need to use the proof of concept that I provide to nullify the G-Security2 pointer. You can just create a script. I'm not creating that here, but you can create a script with and put it in a specific folder, and that script is going to be executed. So you don't need to do anything manually here. Okay, I'm just doing it, and I'm just nullifying the G-Security2 with the proof of concept that I provide you, and now I'm going to execute a Windows UEFI bootkit. But everything that you see here, I don't need to do it. Okay, you just can bring a script with the UEFI shell to do it automatically. Okay, so Avis is executed, and Avis is Black Lotus but on asteroids, basically. There are something strange with this booting, but yeah. So what Avis has done here is it has loaded in the kernel a basic kernel module that automatically has loaded Ventic. And Ventic is a kernel, Linux kernel, a Windows kernel rootkit that we have created and that we have shared last year at DEF CON. I don't know if you have seen that talk, but it was a very good one. So using Ventic, you can hide processes, hide connections, block connections, communicate from the kernel with your command and control. You can do a lot of cool stuff. Yeah, there is a keylogger as well. And here, what I'm going to do is just creating a folder called hide, and I'm going to say to Ventic, I'm going to communicate with this user mode application with the Ventic that is in the kernel to say, hey, I want you to hide this folder, and it hides it. It's just a proof of concept but you can do, at this point you can do whatever you want in the kernel. In fact, in 2 days at DEF CON, I'm going to use in live this Windows UEFI bootkit to drop a kernel ransomware. And CrowdStrike, as you saw, was fully active. It's going to be fully active in the live demo I'm going to do in just 2 days at DEF CON. So just for you to know that this is very, very, very fucking powerful. So let's go with the Linux operating system. Secure boot is fully active, it's enabled. I have to execute a script to configure a Linux kernel rootkit to be loaded during boot. And now I execute another script to bring Antarctic. Antarctic is our Linux UEFI bootkit, and to bring a vulnerable UEFI application. And that vulnerable UEFI application has a custom payloader. So that signed UEFI application is executed, and we have bring Antarctic. So the unsigned Antarctic, the unsigned UEFI application is executed as well because of the custom payloader that is in the signed UEFI application. And Antarctic is going to change the entire boot process. And it's going to disable a few protections that I don't want. So the Linux kernel rootkit that we have configured before with the first script now is executed. So secure boot is fully active on the machine, but using a Linux UEFI bootkit, the first one that has ever been shared, just for you to know, we can now load whatever we want in the Linux kernel. And I don't know what I'm going to do here. I think hiding something. Yeah, hiding just a folder. Well, I don't know. There are a lot of Linux kernel rootkits out there, so you can, bring your own Linux kernel rootkit. The thing is that nobody has ever shared, until 3 days ago, a Linux UEFI bootkit that brings you this new capability of loading rootkits as nothing. So, as I said at the beginning of this talk, today we are going to release everything. We have released everything, in fact. So the research papers on UEFI exploitation, on UEFI bootkit development are there. The notes about CVEs, the vulnerable binaries, the exploits, the debugging workflow, everything is out there for you to practice, okay? The exploitation techniques. You are done with the pictures, or because there's, and we have also released UEFI malware to compromise the Windows and Linux boot chains. ABC's our Windows UEFI bootkit inspired by Black Lotus. We shared it last year. And Antarctic is our Linux UEFI bootkit inspired by Bootkitty that we have shared just 3 days ago in the OFI1 security stream. And this presentation, this PPTX, these images, this everything that you see here, it's in the first one. So you just need to you just need to scan the first QR code you see on the left, okay? So just one more thing and we are done. We have also written a book about UEFI bootkit development and kernel mode rootkit development. It's focused on Windows. Okay, we didn't add the Linux part, but it's we have been using this, the Spanish version of this book for the last 3 years to teach I have been using it to teach students in master's private programs, okay? So it's a good resource for beginners, okay? The digital edition is free. You can scan the QR code and everyone can read the entire book end to end. But a printed edition is also available. So this is the important part of the entire fucking talk. Every dollar we make from the printed edition is donated, okay, to a non-profit organization that supports children with epilepsy and funds research to find a cure to specific types of epilepsy in children. Okay, so if you decide to buy the book, you will be supporting a great cause. Okay, just for you to know. And that's all. Thank you very much for being here, and it has been a pleasure.
All right, ladies and gentlemen, and everyone else, please give one more applause for Alejandro and Maria. All right, excellent talk, excellent talk. We will be taking a little break, and we will be starting with the next speaker, I believe, on the hour. So thanks, everyone, for coming. is a worthwhile thing. If you're not here for Rust, you're probably in the wrong room. All right, today, we now have a couple of speakers who are here to talk about an obfuscator, for Rust. I will introduce them. They're wonderful people. Please, everyone, give a round of applause for João Pedro Tricta and Rafael Felix.
Hello, guys. Hello. So today we'll be speaking about Lyra, which is a LLVM IR obfuscator for Rust. So first of all, who we are. My name is Rafael Felix. I go by the nickname of Biscoito, and I do offensive security research at Hakai Offensive Security, which is a Brazilian company that does a lot of offensive stuff. So I like to do exploit development, Windows internals, Rust stuff, EDR bypass, and previously I did a lot of malware analysis, incident response, adversary emulation, stuff like that. In the past, I did Coffee, which is a COF loader made in Rust, and the proof of concept for the CV 2024-21338, which is a admin to kernel vulnerability through the appid.sys driver. And here, the QR code goes to my LinkedIn, and the GitHub link is there too.
Oh, hello guys, I'm Tricta, I'm 20 years old, and I'm Brazilian too. I'm the client application squad leader and researcher at Hakai Offensive Security 2. And I love reverse engineering, offensive development, sys internals, mobile, and compiler design. I also love programming, gaming. I love cats and pizza. So there is a QR code for my Linktree. You can find my GitHub and my blog in this QR code too.
Awesome. So why does a Rust obfuscator need to exist? Rust is basically getting so popular, especially in offensive tooling. We are seeing more and more offensive tools that use Rust, and nowadays most of the obfuscators target C and C++. There are one or two that do Rust, but the idea here is to make something well-structured and something that you guys can use in your projects just fine, and it works perfectly. So yeah, the Rust pipeline, it's different. Usually, how you do a obfuscator would be through packing the P file or through an LLVM obfuscator, but for C++. But here in the Rust pipeline, it's a bit different, and we are going to show you guys how it works.
So first of all, let's talk around how is the entire cargo and Rust C pipeline to compile a binary. So first of all, we launch via cargo build, and it's just an alias to spawn the Rust C, and it will spawn the Rust C, and the Rust C will perform some steps. So like a normal compiler, it have the lexer and the parser for the front end, and it will perform the HIR, that is a step for desugaring the code. Desugaring is just you get a for loop, the compiler will get the for loop and spread it in like match cases and other things. We have the MIR that will perform the borrow checker it have correlation with the context, so to check the lifetime and the life cycle of the variables and other memory management things. And monomorphization, is a hard word. And this will get the generic types and just convert it to real types like integer, Boolean, and others. And after these two steps, it will get for us the LLVM ER with the type the SSA is a single sign-in, value for registers. Like LLVM have like virtual registers. It not corresponds to the original value of a physical register. So we need to just assign a value for each register. It cannot like we cannot change. Imagine you have an R equal n1 plus n2. You cannot assign the R value again. So it's just need to have one assignment per register. And after that, the optimizer and the code generator for the object file, and it will lead on the linker to link all the stuff and generate the final binary on what architecture you are compiling for. So we call LLVM N2M architecture. So it's not it's more modularized, and you can have multiple front ends like Clang, Rusty, or others to any architecture you want, like ARM or PE files, ARM or x86 files, sorry.
So yeah, why did we choose to specifically modify the LLVM IR? If we try to change the source directly, LLVM's optimizer is gonna delete your obfuscated code, or it's gonna do something bad. So we get right in the middle, behind the final binary and after the source. So if you want to do a source obfuscator, you would do something like in the parser right there, here, with abstract syntax tree. So you'd make a proc macro and put it in the function, and then that changes the function structure, but that goes before the optimization. So when we generate the intermediate representation of the code, we have a more stable and consistent file to modify.
So when we were thinking about to develop Lyra, that is the LLVM obfuscator, we thought in some options, like the common one for, like Biscoit said, of create a LLVM plugin like in C++, but we have some problems, like on Linux and macOS it works perfectly fine, but on Windows the LLVM toolchain of Rust ships LLVM enable plugins off flags, so we can't pass a plugin. It will just silently fail, and we will not get an obfuscated binary. We have some compatibilities issues too, because the FFI of C++ running on the backend need to be extremely equal on the compilation and architecture, and if we like change a little version, like not the LLVM 22 to LLVM 21, it will fail too and not be able to just make all these things work. So our approach was place 3 binaries. One is we have Lyra, that is our CLI tool, that will run the cargo with the Rusty wrapper, that we will talk in a minute. And Rusty wrapper will just filter what crates we are wanting to obfuscate. And after this filter, they will pass to the Rusty, the IR, the Lyra will emit the IR and apply all the obfuscations on this intermediate language of LLVM. And after that, we need the linker. The Lyra linker is the third binary that will perform the linkage things. Have some little points that we will talk in a minute. So
yeah, we will explain why we needed to make a custom linker shim, because when we tried to use the original Rusty linker, it didn't work, especially on Windows, because there are a lot of caveats on Windows.
Yeah.
So yeah, here's another graph which shows where exactly we cut in. So as I've said, we have the source, we have the AST, we have the HIR, the MIR, then we have the LLVM IR. which then we can generate the .ll file, which is the language, the intermediate representation. And then we do the passes. We modify that LLVM IR file. Then we get the obfuscated output here. Then we compile with LLC and CLang. Then we get the obfuscated object file, and then we pass through the linker, and the linker generates that final exe or DLL or anything that the linker does.
So here we have the process to run Lyra on each ecosystem. So Lyra needs the LLC and Clang and the LLVM AR, that is a AR modified version to work with LLVM. This for LLVM 22, that is was for Lyra was built to work with. And on Windows, it have the llc.exe, and we need to create an empty file that is called xml2s.lib, so it can just work fine. So in macOS and Linux, you can just download the LLVM toolchain from the package manager, and on Windows, you can download the pre-built version, and it will work fine.
Yeah, and the idea here is to make something cross-platform. So we've tested on macOS, Linux, and Windows, and we wanted something that worked on all these three major operating systems. And ARM works too, because we are, well, using Rust and LLVM, so we have a broad range of support. And about the XML2s.lib, for some reason, when we try to compile a code with LLC on Windows, it tries to find a symbol from that library, but the shipped LLVM for Windows doesn't come with that library. So if we just create a 0-byte file with that name, it goes just fine.
Yeah, it's no needed to download the original one XML2s file for some reason too.
And on Windows, you also have to download the release directly from their GitHub, the LLVM release. Otherwise, if you try to install the pre-built binary, it's not going to come with LLD or LLVM AR.
Yeah.
So yeah, we have two paths here, archive versus linked output. So for the archive output, we're going to be speaking about the LLVM archive. So when you have a library in your Rust project, that library transforms into a file that's called rlib. And that file contains the object file, which is the compiled code for the library. So when we are obfuscating the libraries, we need to open that package with LLVM archive. Then we obfuscate the IR. Then we replace the unobfuscated object file with the obfuscated object file, and then we put it right again on the library. For the linked output, we have a binary or a shared library, which Rusty calls the linker itself. But yeah, and then we generate the LLVM IR. We obfuscate it, pass through LLC and CLang, and then get the object file, pass the literal linker, and then the literal linker swaps the codegen unit, which when the file ends with -cgu dot, it's the codegen unit that contains the Rust allocators. So you gotta skip that. Then we compile the final binary here.
Yeah, just confirming, the AR needs to be the LLVM IR because the default AR doesn't work with, don't lead with LLVM, so it needs to be this binary.
Right.
So We have three things that we need to force to work properly, the Lyra. So first of all is code gen units 1 is to we just generate a single code gen unit, because if we change a function and we have the randomization, we will see this on the passes, it can generate different functions, different implementations of each function, and we don't want to need to hunt the same function on other file to obfuscate. So it's better we just generate a single code gen unit and obfuscate this only place that have this function and kind of stuff we need. We have LTO off too. It's because on the
link time optimization.
Yeah, link time optimization. And this is because the LLVM on the libraries are libs. We'll ship the bytecode inside it, and we don't want it. We need the raw LLVM IR to work with. And we need to cargo clean, obviously, to not fall into the cache and not generate the code.
Awesome. So, yeah. As I've said, one architecture works both on Windows, macOS, and Linux, because the same Rust-C wrapper is used. So, Lyra wrapper and Lyra linker, they work on any operating system. So the target is going to default to the host target, which you can see with Rust-C-VV. And the real linker is resolved per target. And also, on Linux, we had one thing, which LLC defaults to relocation model static, and Rust-C uses position-dependent shell code, which on ELF, that mismatch is a hard position-independent executable link failure. So we have to force that to make it compile on Linux. And also, on the linker shim, we had some stuff on Windows too that I'm going to show you guys, which are specific to Windows because create process has a 32 kilobyte argument limit, and we have to create a file, and that file gets parsed by the linker, and then it links. So let's get to the passes. I'll start with string encryption, which is pretty basic. So for every constant string, we're going to generate a per byte key. And then, as you guys can see here, the example, we have the original file, which has the allocation for the variable here, which has 25 bytes. Then we define the void main, which is basically the main function. And then we print and then allocate the variable and print the pointer. And then with Lyra, we have the already XORed variable with the key. And then we put the Lyra decrypt stub, which is inside the LLVM global constructor. So it's going to call as soon as the application opens before main. It's going to decrypt all the strings, and then we get the final plain text string on memory. So yeah, this is a compile time string encryption. Doesn't work in runtime. That's an other approach.
Yeah, remembering that the global constructors will run before main. So it will decrypt in some time when the code just coming on and execute.
And then we had some issues with Inkwell because Inkwell is a safe wrapper for the LLVM bindings for Rust, but apparently it's not that safe. We had some issues with the LLVM isConstant string function. It tries to cast to a constant data sequential, but the value is unmatched. So we just get a straight crash. That is not safe at all. So yeah, the fix was calling LLVM is a constant data array is null before, so we know if the constant has a data array or not.
Yeah, this type of structure in Rust, it can be a string or not. It can be like a pointer for some function or just an address. So we don't have pretty sure that it will be a string, so we need to validate this before run the pass.
Great. You can do the shuffle blocks.
Okay. So shuffle blocks, we have this code here, this check off, and we can see we have some basic blocks. And what is a basic block? Basic block normally has a initial and a terminator. We can think on these blocks like the blocks of disassembler, like IDA or Ghidra on the flow graph. So what the shuffle block will do, it will perform an algorithm that we call Fisher-Yates. Fisher-Yates will get the maximum value of the blocks, like here we have 5. It will pick one randomically and change with the maximum value. So imagine the value, the randomic algorithm chose 3. So on the first time, we will change with the 5 block. And if after that, we'll subtract. So we already moved the 5 block, we'll subtract the 4, and we'll choose another randomically and change for this block too. So like after the 3 change with 5, we got the 4 block and change with the another randomic after the 3 until we achieve the very top block. One thing here is it will use the seed, and we need minimum 3 blocks to perform this operation because of the branches and there is no PHI node. So yeah, the result will be that one. So we can check the blocks are shuffled, but these don't change on the disassembler view, on the graph view. It's just more for evade like IARA rules or static rules that can try to search for bytes in the binary. Mixed Boolean arithmetic, MBA. This will get an operation, so like add, subtract, shor, and or the float variations of it, and we will make the equivalent mathematic, but with a Boolean arithmetic logic. So we have we have an example here that is this one, like sum x plus epsilon is the same as we short the both values, because the short of the both values will be the same if we don't borrow the values on the sum. And here we can perform an AND operator that is the same value, but we need to multiply by 2 on this borrow because we are leading with binary. And after that sum, we'll make the same that we just sum x and epsilon. So is the equivalent operation mathematic. Here we have an example. So we have the add I32 and the value there. And after will be like more 6 operations to do the same thing. So we are growing the block.
But it's exactly the same result.
Yeah, exactly.
It's just some junk mathematical.
Yeah, and this is a case that is incredible because if we use it to perform it on the source code, the optimizer will clean and not have this obfuscation. But on IR, the optimization just don't exist, so we can just plain junk operations there. So on MBA, we have 3 variations for each operation, for add, subtract, shor, and NR. And it will pass 2 times on this obfuscation. So if we have a sum, like an add, the add will choose 1, and after for the other operations, it will choose another time. So these 2 times parentheses x or epsilon can be obfuscated again. So it increase more like 10 operations or 15 operations. So we have indirect branch too. And this case, we need to, MBA exists principally because of the second pass that is the indirect branch. Indirect branch, we, instead of just jump for the address of the next block, the next basic block, we make the change of the branch to an indirect branch on a table that will be live in the RO data, the read-only data of the binary. And it will just, instead of jump directly, it will need to consult, retrieve the value from the table, and after that, jump on this address. So if we just perform this pass, if we check on a disassembler, it will get more instructions to perform, but we can still see the control flow graph. But with MBA combined with it, the disassembler can't guess the address, the index of the table that it will try to achieve. So it is more hard, and we can totally break the control flow graph.
So yeah, here we have the example before, which is just using normal direct branches, and with the obfuscator, which is using indirect branch and mixed Boolean arithmetic. As you guys can see, the code is very different.
Yeah, and like we have the indirect branch, and here on the MBA, this address here, it will perform the audio obfuscation of MBA and try be more hard than it is already with the indirect branch.
So yeah, let's talk a bit about the per build seed. You have an option on the CLI of Lyra, which is -- seed, where you can define a seed for the obfuscated binary. So you can make the exact same signature if you set the same seed, even with the obfuscation passes passing through. So as you guys can see, the same source file goes to the same hashes with different builds, and with Lyra build, we get different hashes, but if we set the same seed, we're gonna get the same hashes. And here's a little table on what Lyra beats and what it doesn't. So strings, the defender is not going to see the strings. The strings are going to be obfuscated. So if you try to execute strings on the binary, you're not going to see any of them. On Yara, you're going to get 0 matches too.
Yeah, on Yara, we have the both things together, like 3 suddenly, like the strings one, the shuffle blocks,
yeah,
and all the hexadecimals will be shuffled, so Yara can't match it, and now string too.
Yeah. On IDA, so the control flow graph view, it's going to be very confusing, especially because indirect branch and MBA. Shuffle blocks contributes a little with that too. The import hash for Yara is going to be the same because we're not messing with the IAT. BinDiff, it's going to be quite similar. 0.65 is what we got. Yeah, if you just debug, you can see the strings just fine, as I've said. And then let's get to the reason that we needed to make the linker shim, which is UTF-16LE, bomb response files.
Yeah, the BOM is like
byte order mark.
Yeah, byte order mark. It's like the magic bytes of the file to identify this is UTF-16. So we need to place the FFFE on the beginning of the file. And
yeah. So as I've said, drop the .rcgu.o without the -cgu because it's the codegen unit that contains the restalog functions, and we don't want to obfuscate that, of course. Yeah. Then we'll show some demos.
Yeah, let's go to the videos. So this first one is the strings one. So let me check. Okay. So here first we are building without literal just to compare. It's the plain.exe file. And we will build this same project that is test project with the lira is the obf.exe file, that is the obfuscated one. And we will apply the string encryption here. So it will apply the pass. And if we try iString on the plain.exe, that is the common one, we can check the secret string that is there. But if we try the same thing on the obfuscated binary, it will not have more the string. Where is the folder here? Oh, wait. Here we have Yara rule to detect the shuffle blocks one. So imagine here this is our entire function, and we want to detect if this function exists on this binary, because I don't know, it's a malicious function. Like building normally, the same one is the plain.exe, and obfuscating with the shuffle blocks pass. If we try to run the Yara rule on the plain.exe, it will show there that is detected. But if we try on the obf.exe one, it will not say anything because it can find this is vulnerable, this is malicious, they have the same function.
So we showed the demo B, but I just wanted to show a little screenshot of Hydra here with the indirect branch. If you guys can see here, we have a comment which just says that the jump table is completely vanished.
Here we saw the Yara one. I think I have a cool demo here.
Yeah, sure.
Should we get for Yara? Here. So it's the same example, but it's not shuffle blocks, it's for strings. It will just perform the same action that we saw earlier, but without strings being a Yara rule. So we apply the passes. It needs just the string encryption, not all of them. And if we try to run Yara on the plain.exe, we'll detect, and with the OBF no. And let's go to the chain of the control flow graph. First of all, let's understand the MBA. Here we have the comparison of with MBA and without it. So it's more large, obviously, there. And we can see the operations. I think it's not so clear if we just look all the assembly operations, but we can compare here on the compiler view here. Oops. Here we have 354 lines on the obfuscated one, and on the not obfuscated one, we have the 288 lines.
Just for context, this is a test project that we are testing, the obfuscation. It has a lot of mathematical equations because we implemented a simple FFT function which is fast Fourier transform, just to test it. And we had a good results with the MBA on it.
Here we have the indirect branch standalone. We can see the both graphs. Here is the not obfuscated one, and there is the obfuscated one on the left side. I think is the obfuscated one. No, the not obfuscated one is on the left side. And we can see here the blocks are little, and on the obfuscated one, the blocks are more. They have more operations because of the indirect. It needs to get the address on the arrow data of the table and just load into REX and jump for it. So if we just get a zoom on one instruction here, we can check, like here we have just a simple jump not 0. But if we go on the indirect branch, we need to pass this value to the jump table that it says here that it have the jump table exactly here. But if we combine the MBA with the indirect one, we have a more interesting result, because here we can see the flow graph and there is totally broken. So we have the same blocks, but they are not correlated. And if we check this on the decompiler, we have this view that is awesome. We can't reverse because it's fully runtime.
Yeah.
Have the with the other two. Oh, we have this last one that is the all passes.
Yeah, with all passes.
And this all passes is interesting because we place the shuffle blocks that don't have much impact, but on this case with the indirect branch and the MBA, either just start to hallucinate. It don't knows where to go, so it tries to create a control flow graph that is not the don't make any sense. This like it's just trying to follow in line the operations and make a lot of jumps, but it don't know where to jump. So yeah, that's it.
Awesome. So yeah, I'm here saying the 2 builds, 2 fingerprints. The same thing about the seed. And we plan on implementing more passes, not just MBA, indirect branch, shuffle blocks, and string encryption. We plan on implementing those passes, which are on the roadmap for the repo too. They are passes that contribute with hard reverse engineering of the binary, contribute with different static signatures every time. And there's the cool one, which is the VM-based flattening, which is basically implementing a virtualization inside the project, which is very cool, and we plan on doing it in the future. And that said, I just wanted to ask you guys if you guys wanted to contribute with the project. Everything is structured on the GitHub project. We already have it published, as you guys can see. This is a QR code for it. You guys can test it on your own Rust project, test it if it works fine. And then if it doesn't, you guys can create an issue or just talk to us.
Yeah.
Yeah, and that's it.
Thank you, guys.
Thank you.
All right, thank you for that great talk about Rust and obfuscation. Does anyone have questions?
So how nicely does it play with like the cross crate if I wanted to, compile it on Linux 64 and then cross compile it for like ARM 64? Does it play nice with Lyra?
So I actually haven't tested doing cross compilation, so we'd have to take a look at it. Yeah.
Anyone else? Question? Yeah. All right. Well, thanks everyone. This was a great talk. Thanks everyone for coming tonight. This was the last talk for this room. If you want to talk with the speakers afterwards, you're welcome to. Please pick up your stuff. Don't forget your things. We want to make sure that everything finds its way back to the people whose it is. Thanks again, and one more hand for our great speakers. Thank you very much.